Okay, so you haven't learned much about substrate at Frame yet. This will be all coming next week. And you will be learning how to actually build chains with Substrate, how to potentially build solo chains with Substrate, and then how to potentially connect them to something like Polkadot. What is useful to know, as I mentioned previously, is that Substrate is not just for building parachains. It is perfectly fine to build a solo chain, and there's already a bunch of Substrate solo chains totally disconnected from Polkadot ecosystem that work perfectly fine on their own. It's a generic blockchain building framework. That's why there's also a large community supporting and answering a bunch of questions, issues, and providing tooling for those chains. And if at any point you want to connect to Polkadot, get the extra security, get the extra communication layer, it is always available. And the way to do it is Cumulus. Cumulus is essentially an extension tool to Substrate. It's a bunch of libraries, scripts, and tools that turn your classic Substrate solo chain and allow it to connect to the Polkadot or any sort of relay chain. It's the glue between the Substrate chain and the relay chain. And pretty much every single parachain team within the ecosystem is using Cumulus to connect. I don't know if there are any exceptions to this. It is definitely possible, but it's not something that's common. So we discussed some of the responsibilities of collators. And we will actually be discussing them now. So yesterday, we kind of jumped into a bit of the backing and availability stuff, and we slightly brushed on the collation aspects. So now we'll hopefully dive a tiny bit deeper into that now. This whole pipeline is something we called parachain consensus, or ELVs. There was a nice research paper published by the Web3 Foundation called Machine ELVs, which was essentially a very scientific formulation of this protocol. You can think of it as the formula of how Polkadot rollups work, how they are secured, how parachains can be secured by the relay chain. And as I was mentioning, we have those like 5 main stages where we bundle up collect transactions on specific parachains. We produce collations on the collator side. We send them for backing. We assign responsibility on the relay chain. Then we ensure that the data is available. And then approval, checking, and dispute is something we'll be covering later today. This is where we actually do the correctness verification, the heavy lifting of checking, really checking if it's true on a larger scale. And if it's not, potentially having some disputes and escalations. I linked the paper if anyone would like to read it. Disclaimer, it is relatively math heavy. There's a lot of proofs because it's not just a description of the protocol. It's a formal mathematical proof of its security. So an important question here is just to figure out what even is this state stuff we are talking about. So as I mentioned before, blockchains were often described as big ledgers. And that analogy was pretty dismissive of the execution of the computation part of the blockchain, but it was still very accurate for the state part of the blockchain. State is essentially all the aggregated accounts, balances, a bunch of variables. If you have a game on a blockchain, this is the current state of your character, the current items in its inventory, if you have a character or anything like that. So if Alice has 10 tokens on her account, this Alice account having 10 tokens is literally held in the state. And just to be super clear, it's not just the basic balances and variables. There's some extra stuff as well. If you have a programmable blockchain, smart contracts, the actual body of the smart contract, is also held in the state. So in our case, in Polkadot, as I mentioned, the runtimes of blockchains, the cookbook of a specific parachain, this is held on the relay chain state. It's actually there in the memory, replicated between every single relay chain validator. And this state can be modified by transactions. We primarily in the Polkadot ecosystem refer to any sort of external coming interactions like calls and transactions as extrinsics. They're the external coming information affecting the internalities of the system. So for instance, if Alice sends 5 dots to Bob, it modifies the bit of state where Alice has some coins and now Bob will have some extra. And transactions are just operations on the state. They're state transitioned to a new state. And this is also why everyone needs to keep track of all this state, because to apply the transactions, you need to know what you're actually modifying. You need to have the relevant pieces data to apply the transitions. And in most blockchains, and I really mean most blockchains, this is handled pretty naively. Everyone simply has all the state. This is the monolithic approach. Every single validator has every single piece of state because, well, if I later on will be doing a transaction on the state, I need to have it anyway. There is a full replication, full duplication between all the nodes. So in a world with no state sharding at all, everyone just holds everything. There's a full data replication. And if we have 1,000 items in the state, this is very much doable, and it's not a problem at all. The problems start happening when we approach millions of things, when we reach gigabytes of state. And whenever you are trying to pass it over, whenever you try to store it, there is too much stuff to actually store. And the scale just gets too big. There's too much stuff, too many accounts, too many balances, too many items to reliably store. And this can lead to some kind of centralization, because if there's so much state you need to hold, you cannot run this blockchain on consumer-grade hardware. You suddenly need a supercomputer with terabytes of data and terabytes of bandwidth to actually support all of it. And some blockchains just went this path. They said, okay, yeah, screw it. Let's just require that all validators are pretty much running supercomputers. And an average Joe just cannot do it. But data replication is not inherently bad. It is good. It provides us some security. If one person doesn't have the data, we can always go to someone else. It provides decentralization, which is a very good safety net that gives us, in the end, the resilience I was actually talking about. So we don't want to fundamentally get rid of it. It's still a nice property. We just want to limit how much replication, how much duplication of data we are having. So the Polkadot network, instead of storing its state in one big blob, in one big network where everyone has everything, uses the approach of separating that into smaller islands, into smaller state blobs. It's no longer this one big monolithic storage. It's not siloed into a single entity. And this is partially where all the parachains are coming from. Each small silo of information, each small silo of state is essentially a separate small island, a separate small parachain that has its own custom state that will only be managed by the collators, by the nodes unique and specific to that own little island, that own little parachain. And the nodes of that parachain, aka collators, are the custodians of the state. They're responsible for holding it, maintaining, and providing access to it if it's needed at any point. So just to make sure it's super clear, the relay chain validators, they do not hold the state of the parachains. They are only storing essentially Merkle root hashes of the state. So if at any point some data will need to be accessed from a parachain. Because we have the Merkle root, we can provide the Merkle proof that this data was in fact on a parachain, but it can be provided at a later date. Additionally, the relay chain has some state in it. There are some things we are storing on the relay chain, but the general direction is that we want to minimize how much state and computation we are doing on the relay chain. This is this minimal relay chain initiative, because the less stuff we do on the relay chain, like balances, like accounts, like all of that, the more parachains we can actually secure, which boosts the diversity and throughput of the whole network. Ideally, relay chain, no transactions, no users. And it's super confusing for the people in the ecosystem, because I often see like blockchain comparisons when they say, oh, this blockchain has this many transactions, and they look at the Polkadot relay chain and say, oh, they only have so few transactions. Like, yeah, there should be 0 transactions there. It's completely pointless to look at the relay chain. It's just a security aggregation layer auditing all the parachains. If someone will be looking at Polkadot and wanting to assess how many transactions we have, they shouldn't be looking at the relay chain. They should be aggregating all the transactions happening on all the parachains that are, in the end, effectively audited by the relay chain. Those are the Polkadot transactions. Do we have a mic?
Yeah. In the data that's actually sent to the parachain, does it give anything like a transaction count? Even though it's just, I know it's a Merkle root, so you can kind of get the proof, but does it give like a value that can tell you how many transactions is represented by that Merkle value that's been passed up?
No.
Wouldn't it be useful though?
I'm pretty sure there are other ways of fetching this data and putting that on the relay chain state. We don't need consensus on that. There are other ways to verify that. You can always ping parachain RPCs. You can inspect the parachain blocks to see how many transactions there are. It's not opaque. It's simply, there is no security benefit of putting that information on the relay chain state. Like, we want to be very deliberate with what we are putting on the relay chain state. Like, very, very deliberate. There are blockchains in the ecosystem that are not so deliberate with system messages, and they're sending a bunch of system transactions and messages, and then they're boasting online, look, we have this many transactions where 80% of them are actually system security messages and not actual user transactions. Like, we could be doing that, and we could be putting statistics like that as like a transaction, but it shouldn't be a transaction. It makes no sense to put it there when it's available elsewhere.
I was just thinking the transaction count might be assistive in a fraud proof detection later, in case, like, because you do have the Merkle proof, but you don't have a count. But it's sort of like double checking, like, oh well, if you see over time accumulation of transactions to the relay chain is outside of a certain threshold that's expected, then something maybe a hint that something's wrong and require deeper investigation. So in that perspective, that's why I think the transaction count might be sort of useful to have at the relay chain level.
It could be a reason for investigation, but from the perspective of the relay chain, I don't think they should particularly care how many transactions there are. As long as, from the perspective of the relay chain, it's an opaque blob that needs to be re-executed. There are some transactions, we don't even know exactly what they are. It doesn't matter at this point. As long as it computes in enough time, there's like 2 seconds of computation, and it touches a sufficient amount of I/O and not too much I/O, whatever it is, it's fine. And it's simply not a security necessity to have it there, especially because this information is available through other sources. Any other questions before we proceed?
Hello, Lucas here. So the whole Polkadot network shards its state, but where a parachain shards its own state, it's up to the parachain.
Correct. You could have a parachain shard its state even further. I am not particularly aware of a parachain doing that. You would have to have some kind of a scheme you wanna apply there. You can have, there's a bunch of parachains that have some like off-chain worker mechanisms, and some state they have off-chain, they submit it only when they need it. Very much possible, very much doable, as long as whatever scheme you're using, there is a Merkle root that's, all the state can be in the end proven pointing to that Merkle root, then sure, whatever works.
Okay, thanks.
But also, just to be clear, sharding your state for a parachain is not something many people are doing because there is little reason to do it. The Polkadot relay chain doesn't limit how big your state of a parachain is. You can build it as big as you want, as long as your collators are able to maintain it. The limit is how much state you can touch at a time. So when you're providing a parachain block, if you're doing an airdrop to 55 million accounts and you all want to do it in a single block, probably problematic because you're touching 55 million accounts, which is a lot of state. You need to essentially prove the existence of all of those accounts to make this state transition. So something like that will probably batch over multiple blocks. You can have 55 million accounts in your state, it's just touching them at a single time is difficult. So sharding approaches make it possibly easier because for a parachain, because maybe you're using a scheme where not every single collator has to store everything. But your state has to be stupidly high, and you have to probably have a very big collator network to even consider solutions like that. But it's definitely possible. Any other questions?
I have two questions on state. One is there an easy way to find the size of the state for like various parachains? And second, I know you can like query the state for a certain value, like balances and all that.
Mm-hmm.
Is it possible to just download the entire state onto like your own computer and then look at it in any way?
So I am pretty sure that the answer is yes to both questions. To the first one, okay, so for the second one, to the downloading the state, if you would essentially run a collator for a parachain network, then you will download all the state. You will sync up to the current state of this parachain. You will have in your RocksDB on your collator, you will have the complete state of the parachain, and then you can do whatever you want with it. So essentially, you have to sync up a collator node to that network to get full access to it. And what was the first question again?
Well, the first question was finding out the size. So
the size, okay.
Obviously, if you ran a collator, you could just query the size that way.
Yeah.
So is the state stored on the relay chain or the parachain?
The state of parachains is only stored on collators, and it is not held by relay chain validators.
Okay.
So if you would like to check the size, the relay chain validators definitely do not know the size of parachain state. They only get partial parts of state they need for validating state transitions. If you would like to check the sizes of different parachain states, there are definitely RPCs being exposed for different parachains that give you access to their state, and archive nodes that give you access to their state where you can query it. I would assume they are also exposing some statistics about the state, potentially size. It might depend on individual parachains and what they have enabled. And even if not, you can always go through the route of just syncing up a collator node and trying to measure a state like that. I don't have like an immediate solution of how to do it, but I'm pretty confident there is for sure at least a few ways of getting access to the information. But I don't know of like a nice, easy dashboard where it just tells you how big the state is.
Yeah, because your suggestion, if you want to do that for the entire ecosystem, you'd have to run like 70 collator nodes. Where I was wondering if there was just an API call where I could just get the state.
It's very, very likely that there is the RPCs essentially expose an API like that will tell you this information, but I'm not 100% sure.
Hi, Chris A. Is there a concept of state expiry where there's a TTL, a time to live, for state that hasn't been interacted with for a certain interval?
It's generally up to the parachain to manage their state. So the Polkadot protocol makes no assumption. It just assumes you have some state. If a parachain wants to have a scheme where you have to put a deposit to keep something in state, and then it like has a time to live, and then it decays, stuff like that, it's completely up to them. Usually, I don't think this is a very common approach. There are some deposit schemes for state, but many of the networks have relatively heavy and big collators, and the collator networks are not incredibly big. It's not tens of thousands of nodes, and they can manage the state without any particular complicated schemes. But I agree, to make it like fully nice and robust and safe, there should be something like that for a parachain state to manage it nicely, like TTL and any sort of deposit scheme and stuff like that. Any other questions?
Thank you.
Yep, we will go through all of them.
Like due to the limited block time and size of the relay chain, is there any upper bound on like how many parachains it can support? The relay chain can support. Is there any upper bound on that? Like
Upper bound on what?
or like how many parachains it can support?
How many parachains it can support? The relay chain, 200. It's the number of validators divided by a number of validators in a backing group. So I'm always mentioning that we right now use 5 validators in a backing group. So 1,000 by 5, 200 parachains. This is how many we can support at the moment. There is some breathing room. We could potentially make the backing groups a bit smaller. It has some downsides, but then we can have even more parachains. There are some other schemes where we can have like a second relay chain that has another 200 parachains, and then they communicate. There's a lot of different potential to play around with that. But generally speaking, 200 parachains is like the conservative, safe limit.
Hey, Rodrigo here. Yesterday we saw that during the assignment process, collators get active validators assigned to validate the parachain, right?
Yep.
So the collator sent the latest state to the validators, but eventually these validators get shuffled to other parachains, right?
Mhm.
So how do they catch up when the previous parachains that they were assigned are up to date and basically update the new Merkle route for those parachains? Does that ever happen? Or they need to wait until they get assigned to that previous parachain again?
So the beauty is that the collators don't have to send the full state to the relay chain validators. They're only sending the minimum amount of state needed to perform a single state transition. So the current state routes are held in the relay chain storage for every single parachain. So they know what is the head state of a parachain. Like every relay chain validator knows what is the current head state of every single parachain. It is like a hash of it. And then when you're sending the collation, which has the transactions and the minimum state to a single backing group, they can actually execute like a single state transition, verify that it is fine, get the new head data, which is the new resulting state, and eventually this will be committed on the relay chain state, and the head data will be changed to the new one. And then the next backing group, they don't have to have access to this previous minimal state that was used for the previous state transition. They essentially trust the previous validators that did the state transition, that it was done correctly, and this correctness will be verified in this one of the future lectures we are having on execution sharding. So they are all, the next backing group is also getting the new freshest transactions and the new freshest minimum amount of memory to make the next state transition. So you don't have to have access to the previous stuff except just the Merkle root of the previous head data. Hopefully that's
Yeah, gotcha. Thank you.
Carlos, your question. My concern is about performance. When we query the state, how does it work? How can the network find exactly where the data is and return it fast?
This is completely dependent on parachain specific nodes. From the perspective of needs to fetch some data, you never ping relay chain nodes. You ping parachain specific RPC nodes, archive nodes that are exposed by this parachain. They are either maintained by the parachain company, the parachain ecosystem, the parachain governance scheme, or anything else, and you're pinging them because they are the custodians of the parachain state, the parachain data, and you have to ping them and their RPCs to receive the data back. So it is up to them. If you would use something like PDP, Polkadot Deployment Portal, which is like one-click parachain deployment, then we'll be, and depending on how anyone has any questions about PDP, at the back, there is Dara that is working on that and can answer all of that. And there will be a session on Sunday, I think, where we'll be diving deeper into all of that stuff. And this essentially, this PDP stuff spins up the RPCs and the infra for you. So it's already available and people can access all of that state there. But yeah, when it comes to like performance, this is kind of up to the parachain to manage that. They can have bigger RPCs, more RPCs, bigger archive nodes, and all of that stuff. Any other questions?
Yeah. Hey, Emiliano here. So you said that the state lives on the collator, right? So what gets actually executed by the parachain and what exactly by the collator? The collator is the one that validates and also produces new blocks for the parachain, right? Okay. And what does the parachain do?
So the parachain, in that case, does kind of everything. They do the full computation. So there's a bunch of transactions being sent to the collators. Collators get all the transactions. They produce a new block, and this block is all the transactions sequenced. They literally execute this block. They update their state locally, every single collator node, when they import this block, and they send this block to all other collators in their own collator network. So it's just like in a completely normal blockchain, just like in Bitcoin. They just produce a block, every other collator imports it, and they completely execute the transactions, update their local state, and it just keeps going. Another block, another update to their state, another block, another update to their state. What is different here is that they do more than that. Not only they build the blocks, share them with other nodes, and import them, they also send this collation to the relay chain for extra validation. And this extra validation is where they inherit the security of the relay chain, this shared security where every single parachain is just as secure as the relay chain is. And this is also what gives them the cross-chain messaging and other stuff.
Thanks. Yeah.
Cool.
I was just wondering, how could the relay chain have no transactions if like the parachain needs to send the proofs to all the validators?
So there are no user transactions. There are certainly some extrinsics that still will be present on the relay chain after we move out as much stuff as possible. But ideally, there's only a single special privilege extrinsic that is being run there. And we call this extrinsic, I think it's called parachain inherent. I will probably show it today after some of the lectures. I will actually open like a relay chain block and show the extrinsics there. And probably there will be a single extrinsic called, and it's like system extrinsic. And in this system extrinsic, there are essentially two main things. There is the collation backed call, and there is the collation included call, which has all this data that okay, a bunch of validators backed this candidate, this is their signature, this is the ID of a parachain, and stuff like that. So we cannot get rid of that. This is crucial for the working of the relay chain. This is how it secures all the parachain. This is the minimum amount of data we need to verify the parachains.
If it isn't extrinsic, doesn't it mean that it would eventually be synced with all the other validators? Because I thought that all the validators had to maintain like just like a partial POV. So how do like validators prevent syncing with each other?
Relay chain validators are syncing with each other. But this inherent does not include the full POV. Like this heavy blob needed to verify a parachain is not put in the relay chain state. What we put in the relay chain state, what is in this inherent, is very lightweight receipt that this is the idea of a parachain, this is who signed it, this is who is responsible for that collation. This is which backer says it is correct. But if you want to actually retrieve the POV, retrieve the heavy stuff that we don't want everyone to have, you need to interact with the data availability layer and potentially either ping the backers to get the full stuff or do a recovery from data chunks. So we only put this very lightweight receipt stuff in the state, in the inherent. A lot of Merkle roots and a lot of like this receipt commitments, but no actual heavy data.
Okay, so like each validator receives something different, but they all have the ability to extract all the other data?
So each validator executes this inherent, which has this lightweight receipt data. But it is true that every validator will fetch different data in the end because they're in different backing groups. They're responsible for different parachains at a given point in time. So it's not a situation where every validator does exactly the same. No, each of them is fetching different data. There is some shared state, 100%, but fetching the POVs is not this shared element. It's not in the relay chain state. It's unique to some specific validators on the relay chain. For instance, I'm right now responsible for Akala. Later, I'll be responsible for something else, and it switches around. And there is no syncing in this aspect. It's unique to validators. Any other questions before we proceed? Cool. Okay, so we mentioned parachains, and now we can look a tiny bit more about this state transition stuff. So I mentioned that each parachain has their own runtime. This is this WASM blob. This is this cookbook that defines how a parachain builds a new block, how it can transition to a new state. So collator networks generally have three main things. And when you're building a parachain, you are first of all building your blockchain. You need to set up your RPCs, you need to set up your collators, you need to build your runtime, your WASM, and you need to, the big thing is set up your collator network and all the things it will be responsible for. Collator networks have three main responsibilities. There are three main things you can actually choose. You're choosing your block production engine, which is usually Aura. I think we're discussing through all the questions a few different approaches of what you can do there. You can use something like Babe. You can use no blockchain, no block offering throttling and let anyone produce collations, but it can lead to a lot of forking and is not the best approach. You also decide when you're building your parachain, your network, how to incentivize your collators. Because remember, someone has to run your collators. They are not magically run by someone else. You have to create some incentives for someone to do it. Or you can just run them in your basement, but I think you all understand what are the downsides of doing that. It's probably perfectly fine to start with something a bit more centralized, something a bit more permissioned. You go something with like PDP at the beginning, you have them spun up by parity, and over time, as the system matures, you create some incentives, and you make them more decentralized. And what are the actual duties of your collator nodes? As I mentioned, the main thing they do is they store the parachain state. They are the custodians of the state. They're also listening and maintaining a transaction mempool. They're trying to listen to any upcoming transactions, prune the invalid ones, remove them, prune the stale ones, and once they have a sufficient amount of transactions, and when Aura or any block authoring mechanism the parachain uses selects the collator as a block author, they actually get the transactions and produce a new block. And a new block is just like in Bitcoin, just like in pretty much every other blockchain, it's just a collection of transactions. But then, as I mentioned before, this is not where the story ends. This is where it would end for a classic monolithic blockchain. They just build a new block, distribute the block to other nodes, end of the story. In here, not only we distribute that to other nodes of our parachain, of our mini blockchain, we also send that to the relay chain validators. And we don't send just the transactions. There will be some extra metadata, as I mentioned, that is needed to verify it. And I think it's clear why the collations get sent over to the relay chain to do some re-verification, to get validated and get this extra security it gives us. And I already went through some of those diagrams before, but when it comes to revalidating the work packages, the collations, there could be many different schemes of how it can be done. We could be using some ZK magic, where essentially they don't send the full package of data. They don't send all the transactions to the relay chain. They just send some ZK stuff. This is not how it works in Polkadot. Polkadot and elves essentially leverage a re-execution mechanism where we do actually send the full transaction and we do rerun them to verify their correctness. But the whole magic happens is we don't make it so every single node re-executes the transactions. We try to minimize how many nodes have to re-execute them to get enough safety, enough security without compromising, without doing too much replication of the work. But as I mentioned, we cannot just send the transactions. There is a constraint here because the relay chain validators, they don't have the previous parachain state. They need to get it from somewhere. They need to get it from the collators to actually be able to compute the new state. So when we actually look at the collation, this is what the parachain is sending to the relay chain nodes. We see that, sure, we have the head data, which is essentially the result of the computation. This is kind of like a hash, an ID of the new resulting state from this state transition. But we also have some other stuff. We also have something called a POV. And POV has the extrinsics. This is essentially just the transactions. This is what we're expecting. Transactions are definitely needed for the verification, but there's something extra. This is the storage proof. And in fact, the storage proof is most of the weight of the size of the collation. And this field is the one that contains this partial parachain state. All the fields being actually touched by the transactions, all the executions happening there, that we will be revalidating. So anything read with your transactions, anything changed with your transactions, even if you don't read, even if you don't edit a memory, but you just read it in your transaction, it still needs to be included in that storage proof. And with that storage proof, we can effectively create a sparse Merkle tree of the storage. If a parachain sent to us ABC elements, let's say this is Alice's account, Bob's account, and Charlie's account, and there are some balances being exchanged between them, we don't care what are the other elements. And remember, the relay chain has the root. So if those are provided and we have the hashes of the other elements, we can slowly recreate the Merkle root. So in this case, ABC are the actual items being edited, and the green circles are the extra hashes being provided to us as part of the storage Merkle proof. So there's a lot of savings here because the collator doesn't have to send the extra red data here. It's not necessary for the state transition. It's a pruned, minimized part of the state that is still sufficient to recreate the root. Any questions before I proceed?
So where are the transactions on bridges between Polkadot and Ethereum and other chains outside Polkadot? Where are they stored? And within parachains, if there's a bridge, then are they stored on the relay chain?
Most of them, so there's a dedicated parachain called Bridge Hub, which hosts some of the bridges. And essentially, the logic, the internal logic of the bridge is built into the runtime of that specific parachain. There's a different bridge called Hyperbridge, and this is where this custom logic for the bridging lives, in the state and runtime logic of that specific parachain. This is not something being managed on the relay chain. As I mentioned before, everything we can push to a parachain, we are pushing to a parachain. Like, this is where the heavy computation, this is where the heavy logic should be happening.
So if I find those transactions on the parachain, they will not be found. I'll have to access the bridging parachain, right?
Yes, if you want to use a bridge, you have to go to the parachain the bridge lives on. So if you're using Hyperbridge, you are querying potential Hyperbridge state. If you're using something, a bridge like Snowbridge that is, I think, living on Bridge Hub, you are querying Bridge Hub state. There are, XCM is a thing, and I think, for instance, the Hyperbridge team, and maybe I'll be proven incorrect, they're working on adding precompiles on the Polkadot hub that allow you to interact with Hyperbridge from outside of Hyperbridge. So we can immediately call it with smart contracts on a smart contract level. And then behind the scenes, XCM does all the magic for cross-chain communication to the bridge and then the bridging to Ethereum. So it abstracts away all the complexity for you.
Thank you.
Hello,
Okay.
Juan here. From my understanding in this, the sharding works in a similar way as a RAID 5, where with a few hard drives, you can recover the other one when it's broken or something. My feeling is this is working well when you have a high number of collators and validators storing shards of information. But what would happen if you don't have many of them? The network is small and you lose connection with some of the shards. Can it be recovered later when they recover the connection, or I don't know, does the recovery stops?
Mm-hmm. Are you talking about a specific parachain having few collators, or having multiple parachains with few collators? Like, what exactly is the...
Let's keep it simple. One parachain with few collectors.
Okay, one parachain with few collators. So usually, most parachains, every single collator stores all the state. Like, the data is replicated between all collators. So as long as there's at least one collator, one parachain archive node, one RPC storing the data, you can pretty much always recover everything and continue from there. If there is a parachain that has few collators and every single archive node they have would get lost and somehow the data got corrupt or something, then then this parachain might have a problem, because the relay chain only has the Merkle root. If somehow miraculously someone had like a local copy, then it's nice, and they can later prove it. Hey, I found this copy, I have it, it matches with the relay chain root, and then we can easily restart such a parachain. But
Okay, so the parachain gets stopped until it improves everything, right?
the parachain gets
Well, cannot sync with the relay chain.
yes, I mean, the parachain can continue building blocks, but they have to be revalidated and re-verified by the relay chain
Okay,
to get all the nice guarantees.
thank you.
Because the finality, we'll be talking about it later, but the finality comes from the relay chain. We'll dive into that deeper later.
Johannan here. My question is regarding this picture that you've put up in this slide. So from the perspective of the relay chain, do they need the aunts or uncles of this Merkle tree to, like, do they store it in the relay chain validators for each parachain? Because from what I understand, like when you run the state transition function, you can rebuild the entire state root if you just have the aunts, but you need the aunts, right?
So yeah, so the Merkle root, which is the blue circle, is stored by every single relay chain validator for every single parachain. So if we have 200 parachains and 1,000 validators, we are storing every single one of those. Every single validator from the 1,000 is storing every single Merkle root. But the data of ABC, which is the individual specific state transition for a specific parachain, this is not something that will be held by every single validator. This will be provided to only the backing group responsible for that validator, which is the 5 validators. And spoiler, a few extra nodes later on when we get to approval checking. In the end, roughly 35 validators will have this data for a specific parachain out of 1,000. There is only a small percentage of validators that has this data for a specific parachain, like stored locally for some time. But remember, if other validators would want this data, it is available in the data availability layer. It's just usually not necessary, and only around 35 recover it.
So my second question is, when parachains do a runtime upgrade, they change their code.
Yes.
Which would also change their Merkle tree, but the relay chain also needs to know the runtime. Like they actually have to
Correct.
store the code.
If a parachain is updating their runtime, this is one of the examples when you have to do a relay extrinsic. And this is one example of a relay chain extrinsic that is not going away. You're essentially submitting a new runtime on the relay chain so that it updates, it precedes the old one. And it kickstarts a whole process of updating the runtime, checking if it's correct, checking if it compiles, checking if it's not a code bomb, and a bunch of stuff, and schedules the upgrade at a specific depth, and then actually makes the upgrade. Every single upgrade usually comes with a state migration as well, because imagine you're changing the runtime of your blockchain, and you're changing how you store the data or the data formats, and you also have to migrate some of your data items.
My other question is regarding this minimal relay chain initiative. I'm just wondering, so let's say we move, like from what I understand, like you're moving staking and balances. So these are all pallets, right?
Yes.
And from what I understand, you know, the way that they sit in the trie, they're like heavy nodes, right?
Mm-hmm.
So you could possibly just end up with islands of state when they come from the parachain, because they're not really touching anything else in the relay chain. Maybe you can parallelize things in the relay chain, because you're not really. Let's say if we move the pallet, the balances pallet to a parachain, we move the staking pallet to another parachain, and those extrinsics, when they come in, they're not really touching anything else on the relay chain. So inside the relay chain, you just have islands of transactions that don't touch each other. You could probably parallelize all these transactions, right? I mean, I'm just wondering, like, maybe we can change the data structure inside the relay chain. Is that something that can be done, or?
So one of the problems is that when you're running, when you're importing a block, when you're running the state transition function, this is a single-threaded synchronous computation. We are not running async in those. There are technically possibly optimizations to be had there, and you can check that some transactions never conflict and you could run them async. This is not happening. We are not doing that. Active area of research, maybe, I mean, I'm sure that there are savings in that. But this is simply not the approach we are focusing on right now, because we can simply just put it on the parachain and not worry about it on the relay chain. It's in the infrastructure we already have, and it doesn't require this whole new checking and trying to heuristically predict if two transactions don't conflict and trying to do them async. There are some blockchains that are doing this approach, and it is very promising, but we don't have it right now.
Cool, thanks.
Mike.
I'm just wondering, the 10 megabytes maximum, is it like kind of enforced, or someone would like design his parachain in a way that make it bigger than this, and in this case, what would happen?
This is very heavily enforced. And by that, I mean, if your parachain block has a POV bigger than that, this will essentially be rejected by the relay chain. Like, this block will not be accepted. Your parachain will stall. So when you are designing parachains, you are creating all those things, you have to be very careful to not go over this limit. So if you are doing an airdrop on a parachain and you want to do it to 55 million accounts, it's probably gonna go above the 10 megabyte limit. So you cannot do it in a single transaction. You have to batch it over multiple blocks to make sure you don't go over this limit. And it's a very, very, very common mistake.
And in this case, it's kind of like limit the block size in the parachain itself?
Yes. Yeah, the parachain blocks are limited by two things. They're limited by the amount of execution, like how much it takes to compute the stuff, and how much memory you are touching. There are some parachains that, the input is super simple, but there is a lot of computation. And they're heavily bound by this 2-second compute window. There are other parachains, like an airdrop, that has very little computation, but it's very consuming in terms of the POV. There are ways, just to be clear, to get this number higher than 10 megabytes, but this is generally not something a parachain chooses. But they can do something, and this will be explored in the Agile Coretime lecture, because they can get multiple cores. Because this 10 megabyte limit, remember, is per parachain block, per execution core. If your parachain has multiple execution cores, you can get execution core times 10 megabytes per 6 seconds. So your I/O is increasing drastically.
Okay. The number, like in terms of like the block size, is it like publicly available? I mean, like it's there in the documentation, easily to find, or because sometimes it happen, like you just like find it as a bug, and you start to dig deeper, and you find the numbers. Is it like there we can find, or the maximum numbers?
The maximum number of what?
The block size, that limit how many transactions you can have, all these stuff.
I mean,
This is the total. Like in my opinion, this is the data, which is the hash. Is it correct? The proof.
So the 10 megabytes include the storage proof and all the transactions. This is the whole collation.
Okay. Thank you.
Because this is what will be put in the data availability layer. We are putting essentially this combination of transactions and the minimum necessary, the partial try, essentially. So yeah, this 10 megabytes is not just this partial try. It's partial try plus a bit of metadata, plus the transactions. But usually the transactions are very light, like they're occupying a very, very, very small fraction of 10 megabytes. Unless you're providing some super heavy payload inputs, which is a possible thing for some parachains.
Hi. I want to ask, does the amount of the validator in the baking group is based on the core rented by the parachain, or just homogeneous, or is a 5 of the validator will be signed, become a baking groups?
A parachain has no influence over how many validators will be in its backing group. So it doesn't matter which core you get, and especially remember, they rotate around. So even if we are unlucky and we have 999 validators, so it's a number not divisible by 5. So we'll have a bunch of backing groups with 5, and there will be one backing group with 4. So there will be a parachain that for a short amount of time has 4 validators in its backing group. And this 4 will essentially rotate around different parachains. But it's not like you can buy a specific execution core and guarantee you're having those 4 guys. They're getting rotated around, reshuffled, and stuff like that. So it's best to assume everyone is getting pretty much the same amount of validators in the backing group. You have no control over it, and they will be frequently changing.
Okay, cool.
And it's very unlikely we'll change the number from 5. Like 5 is a pretty good sweet spot. It's definitely not going up. It's possibly going down, but it will be for sure between 3 and 5. This is like the sweet spot. Any other questions? Okay. So, as I mentioned, luckily, the state transition function, the parachain runtime of each parachain is stored on the relay chain. We actually have, each validator has this thing available. We can see the actual PVF here, struct, which holds the code. This is the runtime of a parachain. This is the blob, the logic of that specific parachain. And we have a lot of similar names for stuff. Parachain runtime, we sometimes refer to it as this WASM blob. In the future, we'll have PVM and RISC-V. So we'll be saying PVM blob or something. This is the parachain's code. And this parachain code, which is also equivalent to a state transition function, all of this, same thing, confusing, but many different ways to describe the same concept. And this PVF is essentially just this parachain code and some extra hash, some extra metadata. And the PVF is not just the parachain code. It has a tiny bit of extra stuff. It exposes this extra function called validate block, which we already seen in one of the previous lectures. So why this whole PVF wrapper thing? Why not just the actual parachain code? Why is there this extra function? So the validate block creates essentially a small sandbox environment in which it gets the transactions, it gets the partial Merkle trie, and can run a simulated state transition to get the result. So the input of the runtime validation process is the POV, and the function called in the PVF, which is the validate block. Validate block converts the POV into all the necessary inputs for the state transition to get to the final result. And then this whole encapsulation, this whole wrapper is so that it can be easily stored and run. It provides all the necessary APIs, all the necessary calls so it can be run by the relay chain validators. Because remember, the parachain runtimes, they are coming from the parachains. So we are providing this abstraction, this encapsulation, this wrapping, so it's convenient for the relay chain validators, for which parachain runtimes are kind of this opaque blob they have to run in a nicely consumable and callable format. So if we would actually look at the validate block function, and this is something you can Google in the Pocket SDK and check out yourself, we can see that first we construct the sparse in-memory state. This is not the full state. This is just what we receive from the collator. This is the minimum amount of state. And we do that while also checking that the storage route actually matches what we have on the relay chain state, that this is matching to what the parachain head data should be. We enable all the host function, which is the extra call that will be needed to run the state transition function. And then we execute the block, which is with the given state, run this actual block where all the transactions are, and see what we return after the state transition. We are creating the output, the result of the state transition, and we check if the storage route and the output received here are actually matching, if it matches what we were promised by the collator. So the way to look at it is, on the relay chain, we have 3 parachains here. Every single validator on the relay chain is holding the WASM runtime and the root of a parachain. Then the collators are sending the collations, aka blocks of transactions, and the necessary minimal memory state POV. And then with having all of those items, this can be re-executed on the relay chain. That's the cumulus stuff. Any extra questions about state sharding before we continue? In the back.
So let's say a transaction is confirmed by the relay chain validators. It gets sent back to the parachain, and runtime upgrades happen in the relay chain, because of which the same transaction is no more valid. How does the relay chain communicate it back? And what triggers the reevaluation of the transaction?
So you mentioned that transaction is invalid.
Yeah, because of a runtime upgrade on the relay chain.
So every single re-execution is anchored to a specific version of the runtime. When you're submitting a collation, there should be a strictly known runtime version with which it's going to be run. So when validators are running it, they're not just running it with a random arbitrary current runtime. They know explicitly which runtime to choose, and the runtime is being kept there for a while. So if you're scheduling a runtime, every single validator should know that, okay, from this block height, we're using the new one. If there is a transaction submitted to a collator that was intended for a previous version of the runtime, then first of all, the collator will probably reject this transaction from the transaction pool, because they do some early validation of the transactions. If it somehow is not rejected and they build a block with that anyway, then this collation will be sent to the relay chain validators. And if they see that, well, the runtime is already different, this is incompatible, they will simply, when running the state transition function, say, okay, this collation is invalid, it's rejected. It will not be backed, it will not be included, the availability will not proceed for this block.
So the use case I'm thinking is more like a transaction which has been approved and now it's in the past. and then runtime upgrades happen, because of which that past transaction, it becomes invalid.
There is simply no situation where it can happen in this chronology. So it will, if it was executed with the previous runtime, then it was already approved and final. There is nothing that can be done. Like if there is a runtime upgrade, it doesn't change our past. Like if this transaction was executed with the old runtime, it already happened. A runtime upgrade doesn't make it invalid. It doesn't rewind history. It simply makes it so new rules are relevant from this point onwards. It doesn't change how it was working before.
Okay, so I don't know, yesterday or in a session before, this was discussed that transaction can become invalid after a runtime upgrade.
It definitely can,
about...
and they're pruned from the transaction pool. I mean, imagine you're just like a normal user. You're providing some kind of transaction. Then there is a runtime upgrade, and they're changing how transactions are given. They are adding like an extra field or something. And if your transaction was still in the transaction mempool, then your transaction will effectively become stale and will be pruned by the collators from the mempool.
Yeah, not the mempool scenario, but I think probably I'll find out more which scenario it will become invalid, and I'll get back to you.
If it was already wrapped in a collation, sent to the relay chain and approved by the relay chain, then a runtime upgrade doesn't change that.
Oh, okay, good.
Any other questions?
One simple question is related to like the version of the upgrades runtime. How the validator would know that. I'm just like imagining a scenario where a collateral send a transaction which is valid, and then we have an upgrade, and then another collateral like whatever, like the consensus mechanism, the parachain, but he is misbehaving by sending a valid transaction, kind of like, but with different version, a lower version. So how the validator would know that this block, which is like based on the proof and everything, is correct, but they are using an old version of the runtime.
So in the runtime is stored in the state. If you have Alice with some tokens, and Alice has 10 tokens in the state. If you're updating her balance, you're sending an extrinsic transaction, give 10 tokens to Alice. And then this block is imported by everyone. And the state, the runtime gets upgraded in a similar fashion. There is an extrinsic, there is a transaction you can call to upgrade the runtime to a new version. And every single node, every single collator has consensus. They import the block. It's being shared between all of them. So from this specific block, when you execute it, the runtime for every single collator transitions to the new version, like a new pattern, a new cookbook of how things are updated from this point onwards.
But we don't have a scenario where we have kind of a fork in the parachain itself, where I'm passing kind of like block with old version, like back in the history, and kind of like doing kind of an attack in the parachain, and the validator in this case has a valid proof with a correct, like in this case in the state pass or like map to.
If it's using an incorrect runtime, then it cannot be a correct proof.
I mean, like he's using a correct runtime, but he's just like passing a block, like a back in the history. Instead of block 4, he's passing block 3 before the upgrade, let's say.
I don't immediately see the issue now with what you're describing.
I'm describing a situation where we have an attack in the parachain and the collateral is misbehaving by passing. He's not modifying. He's not like kind of like passing incorrect proof. He is passing an old, like he's referring to a point back in time.
Mm-hmm.
And in this case, the validator will have a correct state proof with a correct POV. VF, and he's kind of like, for him, it's correct. Is it correct?
So the idea is that the collator refers to an older runtime. Is that the?
The idea is like he's just like, instead of, let's say the current block is block 5, and this is where we have an upgrade. So instead of passing the block 5, he is kind of doing a fork or whatever, and he's passing block 4. And in this case, the state had the runtime version, the old one. And how the validator would make sure that this is the latest block or the latest upgrade, just like, because it happened, like it might happen when we have fork or kind of attack in Bitcoin, for example, like if I have the most computational power, I can change the because it's kind of a theoretical, it's hard, but I mean, in Bitcoin, for example, if you have a higher computational power, you can go back in the history and start to change all the blocks. It is hard, it is kind of like impossible, but it might, in theory, it might happen if you have the power. So I'm guessing like I'm thinking of what if we have in the parachain a situation where I have an attack in the parachain and the collateral is passing an old block, like starting kind of like changing the history by, instead of mapping to the current block, he's mapping the previous or the one of the old blocks. How the validator would know?
Sure. First of all, like the situation you're describing has kind of nothing to do with runtimes. It's simply mining in the past. It's creating older blocks. It's using an older parent than the new head. Definitely possible. The thing is, and it's kind of connected to finality. The parachain blocks, once they're finalized, the relay chains are pruning all the other forks and other unnecessary like siblings of those blocks if they're not finalized. And the finality is lagging slightly behind the block production. It's like 12 seconds behind. So sure, you can maybe anchor your parachain block like 12 seconds in the past at most, unless there's a finality lag. But you cannot, like in Bitcoin, start mining 10 hours in the past. First of all, you would have like an insane amount of computation to even do that in Bitcoin. In our case, it's just physically impossible. I mean, the finality will stop you. Everyone else will completely reject your like collator blocks, your collations in that case, if you build on like really old parents. So we are proceeding now to the execution sharding. And just as a reminder, we went through the state sharding of how the state is split, how the collators are getting all the transactions, sending them over. We went through all of that, and now we'll be looking at how the execution can be sharded. Because we went through, well, not everyone can store everything. We have that handled already, but now not everyone can execute everything, or we'll be having the same bottleneck issues like other blockchains. In this specific case, the only actors that will be relevant to us will be the validators. And first, let's outline why we even need to go through all of that trouble. Generally, sharding is just our answer to scalability. And I could say that in general, sharding is solving scalability, but in truth, as many have had already, there are no real solution, only trade-offs. So it is coming with some noticeable costs. Some of the costs are bigger problems with synchronous composability, because now you're having this execution potentially done in parallel. If you are wanting to call one small contract from a different origin, it might be more complicated than it was before. So We all heard that blockchains generally don't scale. But in short, what causes actual blockchains to scale so poorly? Anyone has any idea like what is the issue here? Mike?
What is it?
Hello. Okay. Juan here. Yeah, basically the scalability, decentralization, security trilemma, it's a common problem all over blockchains in general. Basically, you have three corners and you can only choose two of them. The more you try to get close to, and the third corner, you are losing one of the other ones. For instance, IOTA, I remember IOTA tries to scale much more, but at cost of losing decentralization by making validators node centralized, or for instance, Bitcoin. It's decentralized and heavily secure, but can't scale.
Definitely true. So if there's more and more computation when I put on a blockchain, we like having a bunch of nodes. We like having a high decentralization. We like having this because of the resilience and security it gives us. But a similar problem as we had with data. Replication is not bad. We want to have some data replication. And it's similar with execution. We want to have some replication of execution, someone verifying our work. But maybe if you have 50 nodes, it makes sense. But if you get to a network with thousands or tens of thousands of nodes, and all of them have to rerun your execution, this is exponentially scaling how much work has to be done. And then if this computation is even harder, then you're not just running your computation once. You're running it potential thousands or millions of times based on the size of the network and how many loops of that you have to complete. So the main issue is the replication of execution in a blockchain. In Bitcoin, if someone is sending 10 tokens from A to B, it's not being run once. It's being run by every single node in the network. Everyone does exactly the same computation to arrive at the result, to verify its correctness. And surprise, surprise, it works for Bitcoin because the state transition function of Bitcoin is so easy that everyone redoing the work is not the problem. The actual state transition is super simple. The mining is what takes all the hardware. But remember, we don't have it. We have proof of stake, which eliminates this element. So the biggest problem here is everyone checking everything is absolutely sacrificing the scalability for security. So imagine a situation where, it's a bit of an analogy, but I think it will help you understand a few things. Imagine we have a company, like a small startup with 3 employees, and we make some kind of a handcraft product, whatever it is. And we really care about, it's like a luxury product, we really care about the high quality of the item. So at the end of the day, we all look at the products we build, and everyone is checking all the different items for quality. If it's actually meeting our standards. So it's a simple approach that ensures that even if one of the employees is lazy and they produce a low quality product, well, the other people will spot it, will actually find the low quality one and throw it out and potentially punish them. And this is kind of how Bitcoin was working. This is how Bitcoin is working now. Everyone is just rechecking everything to make sure this is correct. And sure, it works, but at what cost? So if we continue this further, and the company actually grows to 100 employees, like, do we just keep going? We make all the hundreds or thousands of bags every day. And at the end of the day, like, you have to check, instead of the 3 bags or whatever, you have to check thousands of bags. Maybe at this point it's working, but what if we go to 1,000 employees? At the end of the day, are you supposed to check all the different bags, I think you clearly see that this gets to a point where it's ridiculous. We cannot check all the products. We somehow have to specialize. We have to only check how much we actually can. We have to introduce new levels of abstractions and new levels of responsibilities. So instead of having everyone check for everything, we only have some people checking for defects, or maybe a small set of people checking only a small subset of bags to find something. And well, if there's only a few of them checking, like, is it providing any sort of safety? How can we then work with that stuff? Instead of just blindly trusting the checkers in that case, we are using them as whistleblowers. They're there to raise an alarm. They're there to actually raise an escalation. So if they actually find a problem, we have a few people checking, and if they find a problem, they raise, hey, I think this bag is actually maybe defective. And then everyone comes over and checks, okay, is it defective? Like, they're really investigating and inspecting. So we can get a concrete answer, a concrete consensus between all the people here that this is correct or incorrect. And this is a case where this escalation is giving us a lot of the safety. We escalate in case we spot something defective. But in most happy cases, if there is no defect found, we don't have to escalate. We don't have to bring everyone to do the checking. This small subset of checkers is enough to not raise an alarm. This already means that it was at least sufficiently okay. And this is like this mechanism that is often used in big companies now. This is how governments are expecting that if there is something shady going on in the company, they need only a single person that will do the whistleblowing. They don't need everyone in the company to say, oh, this is wrong, we are rioting. They need a single guy to leak a document. They need a single guy to give some proof that there is something wrong going on. And how does it all relate to Polkadot? Because if you imagine this whistleblower, you only need a single brave person, and then you can bring down the most corrupt company or completely ruin this fraudulent scheme. And it's very, very similar in Polkadot. We leverage this property of escalations to give us as much safety we can with as little work being done as possible. And generally, as long as we get at least one single honest checker being selected, it's enough if they don't raise an escalation to give us enough security. So even if a very small fraction of the network actually does the check for a specific parachain block, even if there is a single honest guy, this is enough because they will raise the alarm and bring the attention of everyone else. And escalation is the happy path optimization. In most cases, everything is okay. Most parachain blocks, if not all, are generally correct. There's nothing wrong with them. So if there is no issue, only very few checkers are actually necessary. So this solution is incredibly efficient in the real world where the fraud is relatively rare, especially in places like that. And it's worth pointing out that optimistic rollups are also a happy path optimization. They're essentially assuming that it is correct and hoping that if something is wrong, a fraud proof will be provided later. But in here, we are being less optimistic. We are being more pragmatic. We are not just saying, oh, it is correct, and maybe there will be a proof of incorrectness later. We are actually trying to have some people, some checkers explicitly check, a small number of them, and they give explicit permission, explicit approval that this is correct or incorrect. And they can raise an alarm explicitly, quickly. So if there are issues due to an escalation, everyone will come in and actually do the checking. In this case, this means that we temporarily break the sharding. The sharding, the execution sharding, is only there in the optimistic happy path. If there is something suspicious detected, if there is some computation that is potentially fraudulent, then we raise an escalation, we break the sharding, and this is because security is paramount. Then we need to get consensus, we need to get everyone to verify and come to a conclusion, a verdict of correctness. So we are willing to temporarily slow down the chain to maintain this absolute security. Okay, so now that we have the core principle of sharding and the escalations, let's see how it manifests in the ELSE protocol. So ELSE, which gives us the execution sharding, depends as a prerequisite on this collation, backing, and availability. All the execution sharding is actually happening in approval checking. We could be naive and just make approval checking be every single validator on the relay chain checks. We have the POV available, and they all have the head data. They all have the relay, the parachain WASM runtimes. So everyone can do the checks. But well, the whole point is, how can we do it so not everyone has to? And one important note about this whole system is that it runs asynchronously in multiple threads on the same validator. So a validator, the whole ELSE protocol, a validator can be in a backing group for a specific parachain while being an approval checker for a different parachain or even for multiple different parachains. Each of those is a separate process, a separate submodule you have running on your relay chain validator. And all of them can happen at the same time. Okay, so let's actually dive deeper into approval checking. Any questions about the prerequisites so far? Not just approval checking, because we'll be explaining that in a second. Mike here.
Yeah, I just want to recall the statement you had in the first slide, I think, that this is not a solution. There is no solution, there is a trade-offs. So my question is yeah, this is a very interesting thing. We are sharding the business by having parachains, and we are sharding the storage by having sharded storage, and we are sharding the compute by having this sharded execution things. What are the trade-offs? What are the pain parts here?
The trade-offs are, if you're sharding the state and you have one parachain that wants to communicate with another, it's not as simple as just calling it. You have to use XCM. There's an extra layer of abstraction you have to interact with. It's adding extra complexity.
And the development layer, or even the time.
So it's adding latency for the user, and it's adding complexity for the developer. It's coming with heavily increased throughput and other benefits, but there are definitely costs to that. Any other questions? Be good. Question there.
I already have a mic. Yeah, I just wanted to double check with you. From my understanding with what you have just explained about how to say it, how does the trilemma works in Polkadot? Polkadot sacrifices a little bit more of security instead of decentralization to improve the scalability. Is it?
I don't think we sacrifice security. I think the best way to put it is we definitely sacrifice some synchronous composability to get everything else. And synchronous composability is not in the trilemma. We definitely added an extra dimension and sacrificed something else to get some of those benefits. So security-wise, I think we're in a perfectly good shape. Decentralization one, better, if not it's pretty much certainly best out of all the possible rollups out there and sharding solutions. But the main thing is synchronous composability. Is, if you have a parachain that wants to call a different parachain, that wants to call a different parachain, a different parachain, XCM message for every single one, it will add a bunch of extra latency. This is something that we are kind of sacrificing here. Jam will probably make it a bit nicer, and Polkadot Hub will also make it a bit nicer, because we're trying to move a lot of the functionality from relay chain and some very popular parachains to a single big parachain, where you'll have staking, governance, balances, identities, all in a single place. So you don't have to XCM for every single little thing, and you can synchronously compose within that one big shard. And then we scale that one big shard with Agile Coretime elastic scaling, so it takes multiple execution cores and have a much higher throughput than all the other rollups in the ecosystem.
Yes, but if not every node is executing every block, aren't that sacrificing a little bit of security? Because
very good question in like 5 slides, because I literally have this question on a slide and I will answer that. Cool. Continuing. So approval checking is, I think, the most important part of the ELSE protocol. Like, this is where the actual magic happens. This is the magic sauce that makes those parachains be an alternative to something like optimistic rollups or ZK. This is the unique part. And one of the prerequisites is that we only start the approval checking process on parachain blocks that have been included on the relay chain. So if you remember, we are talking about a collation coming from the collators to the relay chain backing group. Then they're backing this collation, and it's getting backed on chain. We see, like, later on I will show an event on the relay chain that this specific collation was backed. After it is backed, we are starting the availability process, where we are sending all the availability chunks. And once enough availability chunks are distributed, this candidate becomes available and it gets included on chain. This is another event added by the relay chain block author that marks it as included. So if you would observe a relay chain, you see that every single parachain block gets first backed and then included. And after inclusion, we start the approval checking process. So, just as a reminder, at this stage, what does it actually mean to validate a parablock? This is the same process we went as with backers. But instead of getting the data from collators, because remember, the backers actually just got the full package from a collator with everything ready, the approval checkers are not the backers for that specific parachains. There are some potential other validators. They don't have access to all this information. And this is exactly why we needed the data availability layer. This is to potentially guarantee that this data can be made available to other non-backing validators. And we'll be using the same process as before. We have the PBA, we have the POV available on the data availability layer. So we recover the data, ideally by pinging the backers and just fetching the whole thing. If not, recovering from availability chunks. We have the previous head data, we have the runtime, and we just rerun it, we re-execute. And in the end, when we do it, we will get an answer. It's either correct computation with all those inputs and outputs, or it's not correct. So the whole approval checking process, like figuring out who is checking what, like what am I supposed to check as an approval checker, has this first round we can call a kickoff. Whenever we spot some included parachain blocks, we then move to something we call a tranche assignment. Essentially trying to figure out, am I supposed to be checking it, and when am I supposed to be checking it? And remember that a relay chain block there are many parachains. So a single relay chain block contains many parachain blocks included in it. If we have 200 parachains, we can expect that a single relay chain block has 200 parachain blocks included in it, every single relay chain block. And we will repeat the same approval checking process for every single parachain block. So how do we figure out if we are actually checking and re-executing something? Imagine you are a validator that wasn't a backer. Everyone essentially generates a random number, and this will suggest, this random number will essentially suggest for how long you have to wait before you re-execute this parachain block, before you rerun it, before you re-verify it. This essentially makes it so eventually, technically, everyone will check this parachain block, but it's staggered in time. And the optimization comes from, there is a threshold of how many confirmations we need. Everyone will check it eventually, but we are not waiting for everyone to check. There's a limit, there's a threshold of how many people we want to actually confirm and verify the correctness. And if we are scheduled for a very late check, we have to wait for a long time, and there was already enough checkers before us, we never even get to do the check because there was already enough of them. And then we save on this computation. We're scheduled to do the check, but our check wasn't crucial in this case. So if we would actually look at the VRFs, if we have those VRFs, everyone is running the VRF, everyone is getting this random number. The idea is that first, the lowest numbers will be the ones starting the checking first. We say that they are in the lowest tranches of the checkers. But over time, more and more people with higher and higher numbers will actually start checking. We try and bundle up the checkers into smaller groups, the smaller tranches. Each tranche is generally, on average, around between 2 and 3 validators. They can be slightly smaller or bigger. And because we are using a VRF to generate it, you yourself, as an approval checker, as a validator, you know for a specific parachain block in what tranche you're scheduled to check it. But you just generated a number locally with a VRF. And you don't publish it immediately. No one else knows in what tranche you are the checker. Maybe you are in the last tranche and you will actually never really check it. Maybe you're in a really early tranche and you will do the check quite early. And just to make sure this is clear, every single active validator is in some tranche for every single parachain block. That doesn't mean that they will do the checks, but they are scheduled to potentially do them at one time. And the protocol is parameterized in such a way that we only require around 30 approved statements, essentially 30 validators saying that this parachain block is correct. If we get to this point, the approval checking process is halting. Its job is done. All the other tranches are not proceeding with their checks. They will say, okay, we already had enough confirmations. We are good. My check is not necessary. And this happy path optimization is saving us the computation because not everyone has to rerun it. Not everyone has to recompute it. Only the small first subset, the small first tranches were enough to already give us enough confidence. And if you get 30, we know it is considered approved. But what if it's actually invalid? What happens then? So this is kind of the moment we've been building up. If at least one of those 30 checkers decide that whatever I have checked is incorrect, the state transition here is invalid, someone was trying to double spend, like Alice is sending tokens to both people and they are the same tokens. it is time to actually escalate. It's time to raise the problem and publicly announce it. And the node will then send a special message called a dispute. They will start a dispute, an escalation. And we'll cover the actual consequences of an escalation in a second. But for those wondering, like, what if all 30 checkers are malicious? Then we're absolutely screwed, right? This is a problem. If none of them actually raises the alarm, this would be pretty bad. But even if a single one is honest, then we're good. They will just raise the alarm. So how high do you think the chances are that all 30 are compromised, all 30 are malicious? Anyone particularly concerned? Because I think one of the questions from here was that, well, we are sacrificing some security. And the answer is, yes, we are sacrificing some security, but essentially the chance that, assuming 1/3 of the validators is malicious, this is our Byzantine assumption, like the chance that all 30 are malicious is 1 in 200 trillion. Like it doesn't immediately see like this, but it's just 1/3 the 30th power. Like all of them would have to be malicious. And 1 in 200 trillion, I think, is a pretty good chance and a pretty good confidence margin. So yeah, we are sacrificing some security, but it's like 50 decimal places after. Like it's such a small amount of security you're sacrificing that it's not worth to do all the checking when already 30 validators checking gives us this much of confidence that it is okay. And I think there was a question. If we have a mic somewhere here.
I guess the drawback seems like now that even if one validator maliciously wants to slow down the network, he just has to submit a dispute. But I guess it seems also a problem that if you're slashing validators for disagreeing with the majority, then no one will want to be honest. I mean, no one will want to be honest if they're the only one who's honest.
So you're definitely correct that you can, this is the happy path optimization. And how you break the how do you break the happy path? You start an escalation. This breaks sharding, and as I was saying, if you will do it, you will be slashed. If you essentially start a dispute saying a candidate was incorrect, like a collation was incorrect, you force everyone to do the checking. Then instead of the 30 guys checking, we will have 1,000 guys checking. This is a pretty expensive thing to do. We don't want to do it. You will get a minor slash for it. We call this a spam dispute. You're essentially saying that it was invalid when it was valid. The slash, I think, is very, very low, but it essentially removes some of your validator privileges to be slashed anything. And it will noticeably lower your rewards as a validator. So it's mainly an opportunity cost. If you start spammy disputes, you will lose a lot of your rewards. And it has costs associated to it. And the other thing you said was, there was a second part of your question / comment.
I think I was just, I think you addressed it. I think I was just wondering, like, why would someone want to be honest if...
Oh, okay. Why would someone be honest? Because they're getting paid. If someone participates in that system, if someone submits those statements, if someone is checking that stuff, then you are getting rewarded for it. And what you can do if you are particularly smart right now is, oh, I will just blindly approve everything. I will just say it's correct without actually checking. And you will be flushed. Because if you blindly approve, this is a lazy validator case. And this is actually something I'm working on, like all that approval checking stuff. If you are a lazy validator and you blindly approve, and if you blindly approve an incorrect block, you will also be slashed. It's not 100% slash because you're a secondary checker. The main person being slashed will be the backer. They're, being essentially the sacrificial lamb 100% slash, but you are being punished for being lazy and not checking, and you will get a 2%-ish slash of your stake, which is like a slap on the wrist. I mean, 2% of a few million dots is still noticeable, but it's not a death threat situation. Like you can still recover from that. Okay, any other questions before we proceed? Mike?
I have Mike here. Thanks.
Okay, good.
Just like if you go back to the graph slide, it's mentioned that even you verbally mentioned that the validator who checks, he knows his slot, the other do not know, and I can see there is a VRF here. So my question is, the slot assignment is randomly like assignment, or it's kind of like I can predict, it's predictable.
We are using VRFs, so verifiable random functions.
So the number, like, because the way I understand it, like there is like a source of like whatever salt, and then with a private key wherever, and then we are getting the random number. When exactly the validator would know this is their slot? Because what I'm asking this question is just like, it might be wrong, but my assumption is like, maybe there is like a kind of malicious behavior where I know ahead of time that I will be assigned to this chunk, and
you will know your own assignment in advance for a bit, but to get it, you're using your private key to generate which tranche you're in, and you absolutely, even though you will find a situation where you are in tranche 1 or tranche 0. Okay, I am the checker, but you have no idea where are the other checkers. If you have a bunch of other validators that are also malicious, you don't know, it's very difficult for you to predict if there are no honest guys in the early tranches.
The chunk here or the tranche here is like part of the block or a group of transaction, and we are validating these kind of transactions valid against the Merkle proof.
No, this is an abstract thing that lives off-chain. This is not transaction. This is something each node generates locally. They compute the VRF, they figure out what tranche they are. So the flow is they observe the relay chain state. They see that the relay chain block alpha has included a parachain block. When they included a parachain block, they get some metadata from that, their private key, some source of randomness, and they generate the tranche number. And they hold the tranche number locally. And the tranche number essentially specifies when they should wake up and start validating that specific parachain block. And by validate, I mean start the availability process, the availability recovery process, get the runtime for the parachain, rerun the state transition function, and publish the result to others.
Okay.
There's the only thing that is a transaction here, and eventually will like end up on chain, is if you actually do the whole verification process and submit your result.
The way I understand it, it's an actual block, and the block has the block header and the block.
No, it's absolutely not. Like okay, I use squares here. It's not a blockchain, but everything that has like arrows and squares is a blockchain. This is not a blockchain. This is a timeline. You can think of like every single square here is like 100 milliseconds. Like those guys are checking at x plus 0. Those guys are checking like x plus 100 milliseconds. Those guys are checking like x plus 300 milliseconds and stuff like that. This is a bit of a timeline diagram. And it's essentially splitting all the validators into those like time slices of when they will do the re-verification, the revalidation of a specific parachain block. Any other questions about this process?
Hi, Krishna here. Not about this specific process, more about like dispute. So what are the like consequences of dispute, irrespective of it being a valid or maybe just a malicious dispute? Do we just maybe delay the block formation, or is it more in terms of recomputation?
Mm-hmm. There will be some slides about disputes in a moment, so I think this will be suitable to discuss it then. And if there are still remaining questions, we'll get back to it.
Yeah, sure. Just one more question. So we are still considering the parachain blocks, right? We haven't formed or reached the relay chain blocks. All these computations, all the checkings are happening on the parachain blocks.
No.
These are relay chain.
It will show up in a second. Give it a moment. Spoiler, no collators here. Validators. Everything I'm talking about here, we're talking about relay chain validators. Like every single lecture I'm giving has this like actor moment slide at the beginning. Like this is creating the context what we are talking about. We're talking about relay chain validators revalidating stuff, giving us actual security guarantees. So no, collator's job ended on giving us the collation. Now we are deeper into the ELV's pipeline. Like collator's job, parachain node's job ended on the collation phase. They passed over the data packages, the POV and the transactions. It got assigned responsibility in backing, which is on the relay chain. Availability happening pretty much on the relay chain is the relay chain validator nodes holding the extra stuff. And now we are still on the relay chain, the approval checking, where the relay chain validators, after responsibility was assigned in backing, are doing the secondary checks to actually verify correctness and potentially punish people if it was incorrect.
Okay. Yeah. So maybe like my question was, do like all the process of approval, is it happening for individual blocks that we received from the parachain, or are those, or have we like combined all the parachain blocks that we received into a relay chain block? So these computations are still happening for individual parachain blocks, right? So this process happens for all the parachain blocks that we receive, that the validators receive.
It happens for all the parachain blocks that have been included, which means they have successfully went through the backing phase. Someone took responsibility for them. Then the availability completed, aka availability chunks were distributed successfully. And the next relay chain block alpha marked that availability succeeded. And only then we are starting this. But yeah, this is happening for every included parachain block, which if we have 200 parachains, every single parachain should have an included block every 6 seconds, every relay chain block. So yeah, like it's happening for every single parachain.
And it is happening parallelly with the core shifting that we are doing. So
Yes. Yeah. So as a validator, as a relay chain validator, I am at a specific point in time in a backing group for some parachain. But at the same time, while doing my backing responsibilities, I am also generating tranches for every single parachain block. And there's 200 parachains, for instance. For most of them, I will be in pretty late tranches. So I will schedule wake-up calls that, okay, I have to check this one after like some amount of time, this one after some amount of time. This one I'm actually checking very soon. So I will start fetching the data for this one and we'll do the job. So it's all happening async, even for a single validator. Make sense? Do we have a different mic? I think it's... Thank you.
Right. And in case of a dispute, if possibly maybe the time overflows for these specific like set of active validators, do we maybe extend time, or how do we like handle time in those cases? Because obviously, like in case there's a dispute, everyone will have to like compute all the things. So
yes, when there is a dispute, everyone has to compute everything, which adds a lot of extra load. We have some back pressure mechanisms that when there is a bunch of disputes happening, other things can slow down. One of the first things that slow down is relay chain block authors stop adding backing statements on the relay chain. So essentially, parachain blocks will be skipped. It's like sometimes skipping blocks. This is due to the overload of other more important security-related issues. Other things will slow down. If we get lower pressure there and the disputes stop, then we resume that.
okay, yeah, got it. So like an active set of validators won't complete or like we'll plan as such that they won't leave maybe any process in between. We'll let them at least reach up to a block finalization, and then they maybe like shift over. So that's what I understand. So is that correct?
Like shift over, you mean?
Meaning the next set of active validators come in.
Wait, what was the question?
Right. So my question was, so consider like we are like in a tranches state, and there are maybe possibly there are like some steps yet remaining for the relay chain block to form, or the checking to happen. Considering like there's a end of like their active sessions, do we like skip all the processes further, or do we like hand them over to the next set of active validators?
Okay, I see. No, generally speaking, we do not hand them over. Like all the tranche stuff, all of that is relevant to that specific time slots and the authorities at that specific point in time. Because the authorities, you are the authority not for 24 hours on like a real life clock and then you unplug the machine. It's in blocks, like all the time from the perspective of the blockchain is in blocks. So they are the authorities for that specific block, for that specific time slot, and the tranches are for that specific parachain block included in a specific relay chain block. And the authorities are well defined for that specific relay chain block, so there is no ambiguity there.
So it would like always end with the relay chain block being produced?
It will always...
Because then time would be calculated based on the block production.
It will always end in a relay chain block being produced. What is it?
The active session.
The active session is 4 hours. What does session have to do?
Active session of the or the set of active validators, the time for them, the active validators, it would end with a specific block being produced.
The active validators are active for 24 hours. There is 14,400 blocks being produced in that time span.
Right. So exactly after those number of blocks being produced, they'll end their active status.
Correct. Exactly.
Yeah, got it. Thank you.
And then it's like the point in which the authority switch is well defined in blocks. Exactly after the penalty blocks, they switch up to the next session. There's a rotation of keys, they switch over, stuff like that.
Got it. Thank you.
Any extra questions before we proceed?
Is there a possibility that a single validator could be in the same tranche for more than one parablock? So like, for example, at the 100th millisecond, as a validator, I'm going to be approval checking for this parablock and this parablock at the same time?
It is absolutely possible and is quite undesirable because you can just get very unlucky and be in a low tranche for like 50 parachain blocks. And that is kind of unfeasible to do. Like if you have reference hardware, you will not be able to complete all that work. It will be too much. In this specific situation, it is okay for you to simply complete as much work as you can and ignore the rest. And it's okay because it really shouldn't happen. It's random numbers. If you are, randomizing between 200, generally the distribution for most people will be somewhat equal, and things like that where you are suddenly to 50 parachains are incredibly, incredibly uncommon. So uncommon that we don't have to particularly worry about them too much.
So there's no like any slashing that will happen in case you're not
There
able
is
to.
absolutely none. Yes, it is perfectly okay for you to just not check it. An honest node that is not tampered with and not hacked will do as much checking as they can. But also, if you don't do the checking, then you will not get the rewards. You will only get the rewards for the checking you actually do. But a normal node will do as much checking as they can, and they will collect enough rewards, so it's not a problem. And also remember, there's you're randomizing on which tranche you are checking for every single parachain block, every single relay chain block, and there is 1,000 validators. So there's so many different layers here that over time, it really averages out, and those fluctuations are not noticeable. Anything?
Yeah. If the validator is not checking, will that not be a no-show kind of thing? Like you just said that it's okay if they don't check it.
I will be talking about no-shows in a second, like 2 slides ahead. Any extra questions before we go to disputes and no-shows? I hope it's not a question about disputes or no-shows. It is fully automated. It's not like they're pressing buttons, I'm in this tranche. Like they don't have to think about it. Validator just runs the software and it happens, right? We're waiting for a new mic, but what's the question? I will repeat it.
If you want to be, want to be lazy checking, do lazy checking, then you have to modify the given code. Hence
if you want to be malicious, you modify the code.
Yeah, validator code.
Correct.
Validator node code. Yeah.
Yes. I mean, there are some modifications you can make to the validator code that wouldn't be malicious. If you randomly optimize something and make something faster, sure, this is a modification, but it's probably perfectly okay. There are some modifications that would be malicious. For instance, you can be a lazy validator, and instead of, you can hack the PVF, and instead of checking if it's valid, you can just say everything is valid. This would be an example of a hacked validator node that tries to be cheeky and not do all the work, but get the rewards. But then you're essentially exposed to slashing. If there is ever anything incorrect, and because you blindly approve, then you might be slashed. Okay, we good? Cool. Okay, one extra thing. Do I cover it later? I don't. One extra thing. Why are we using VRFs and generating in which tranche you are in secret? Like, what is the reason here? Why aren't we just announcing publicly in which tranche we are? Anyone sees an attack vector?
Yeah, there might be like possibly a DOS attack on them if we have it.
Exactly. Usually if there's something secret here, I feel like it's the 5th time, and the answer is just DOS. Like, we want to be resistant to DOS attempts. We are super, super afraid that if it will be easily identifiable who is in the lower tranches, who are those 30 guys, then you know exactly who to attack. And you could DOS enough honest people that there are eventually 30 malicious guys. So that's why it's not just eventually 30 malicious. Generally, the first 30 have to be accepting, they have to be honest, they have to be, approving that block. It's not just any 30. So if you're running a malicious node, you cannot be in tranche 50 and say, yeah, I approve it. And then a bunch of other random malicious people from high tranches saying also, I approve it. This will not be enough. It's not just any 30 people. It's validators from the low tranches that were randomized to do the checks. They are the ones allowed to produce those statements. And even though it is not immediately know who is in what tranche, we have to eventually announce it. And even if we don't announce it so willingly, remember, the validators, the approval checkers, they don't have access to the POVs, they don't have the data. But to rerun the checks, they have to fetch the data, they have to reconstruct the necessary POVs from the data availability. And if they would suddenly start reconstructing a POV for a specific candidate or a specific parachain block, this is kind of already announcing, hey, I am the checker. So if you know you are in a specific tranche, you don't start downloading the data early. You wait until it is exactly your tranche, exactly your time, and only then you essentially reveal publicly, hey, I am in this tranche, and now then, and only then, you start downloading the necessary data. You start fetching from availability the necessary elements to rerun the state transition function. Because at this point, you're announcing, okay, I will be checking. And why do we have to announce that I will be checking, I will be downloading the data? If we wouldn't announce it and someone would track it and try and figure out that this is you, they could possibly DOS you before it's even known that you are in this tranche to everyone else. So first is the message, hey, I am checking and I am in this tranche, and only then you start downloading. And in this situation, the hope is, if the slide updates in a second, the hope is that if you announce you are in a specific tranche, for instance, tranche 1, and you are downloading all this data, you can still be DOS. There is still a short opportunity window to actually DOS you. So we haven't fully eliminated the DOS angle, but we limited its potential damage. To fully eliminate it, or at least mitigate even further damage, is if after your announcement, you download the data, and before you publish your statement, so either correct or incorrect, if you disappear, if you no-show, this is suspicious. Because why would you first announce I am checking and then never produce the result, never say correct or incorrect? We, in this case, essentially assume that you were DOS. We assume that you were essentially attacked and targeted by someone, and that you were not allowed to publish your result. And to help with this situation, we have this system that's like a bit of a hydra. If you DOS and shut down a single validator, even more validators will wake up to do the checks. So if there is a single no-show, it makes it so we need one extra tranche of validators. Instead of stopping at the limit of 30, because there was a no-show, someone said they will do the check and they never did, we are requiring 30 plus one extra tranche. So we are replacing a single shutdown validator with on average 2.5 validators, because this how many fits into a single tranche. So this is this hydra. You cut off one head and 3 more show up. Question?
I'm just confused about, because you mentioned, I think a few minutes earlier, that it might happen that we are skipping some blocks. It might happen that they can skip some work. And now we are very concerned about the DOS that might happen. So, like, is there kind of like a time frame? Like, I just like to understand this part. Actually, I'm confused. It's not a question.
Okay. So when I was mentioning the skipping, it was a back pressure mechanism that skips the inclusion of some parachain blocks. The relay chain blocks are still continuing as normal. It is simply throttling and bottlenecking the throughput of a parachain. It's making less blocks. In here, we are very concerned about any sort of dosing and skipping of the work, because if some work is skipped, in this case, in approval checking, this can make it so we get 30 malicious approval checkers. Skipping parachain blocks is a liveness issue. It's a matter of, okay, for a second, we are not producing anything. Skipping work here is a security issue because we can potentially approve invalid state transitions. This is much, much, much more dangerous. Like liveness is important, but security and approving invalid transactions is much worse.
It is because like we trusted that the backer submitted a valid block, and we need to do another like check. Is it correct? It is because like again, it is because like we trusted in the first place, the first step. We trusted the backer that they are behaving correctly, and we included it in the block. And after the data, storing in the data layer, we need to double check that to make sure that this backer wasn't misbehaving. I'm getting correctly?
Yeah, you're getting it correctly, but it's precisely because we do not trust the backer. This is why we're doing the additional checks. The backer was essentially only there to be to vouch for the block. He's the person that's on the hook for the rewards and on the hook for potential punishments. And now the approval checking process, which we are discussing right now, is where the verification of whatever backer said is actually happening. Like in the end, this whole scheme, it's either ends in checking and approving whatever the backer said that, okay, it is actually correct, or it ends in a dispute. And the backer will be slashed. There are no other alternatives. So this is the court date. The backer says, okay, I think this is correct, and now this is the jury. Now we're actually checking that it actually is consistent. Any other questions?
Hi, Luca here. So one question about that number 30. Is it for 600 validators or 1,000 validators?
That's the good thing about this number. It doesn't matter.
And why doesn't
it's disjoint. The only property we actually care about is assuming 1/3 is malicious, what is the chance that all of those 30 are malicious? So if we have a total of 1,000 validator, if we increase the number of validators in Polkadot, we do not change this number 30. It stays consistent. So that's an amazing property of this whole like parachain cynical rollup scenario, that no, it's just the 30 people doing the checks. I mean, the backers plus 30 people doing the checks. And it doesn't matter how many other validators we have. And this is the asynchronous aspect. We can have many, many different parachains, but the number of checkers is pretty consistent and fixed. Any other questions?
Why does the why does the validator need to broadcast that it's doing the check? Like why is it like letting everyone know and then we're afraid that it's going to get DDoSed?
Because if you wouldn't broadcast it, you would still soft broadcast it by recovering from availability. Because you need to recover from availability, the POV, the list of transactions, all the things necessary to actually rerun, revalidate, do the PVF, parachain validation function to get it. And maybe the backer you're pinging is actually malicious and he was waiting for you to ping him and then he DDoSes you. You need to announce to everyone else, to all the honest nodes, hey, I am putting myself at risk here. I will be doing the checking. but if I disappear, cover for me. Because they can essentially find, if you don't announce it, they will still probably find you because you need to recover. So it's better to make everyone else know that, hey, like cover for me if something happens.
Thank you.
Any more questions?
As a process, each validator will do their job to verify once, whatever the block already passed the threshold, right? So if some bad node do the validation, although the transaction is valid, but it result as rejection, we will mark those node validator as bad actor, and any penalty on those. Do you get my question? Sorry.
No. Slower.
Okay, I try again. Sorry.
Let's. Yeah.
Okay. First, my understanding is the validators will do their job whatever already match the threshold of create the block.
The validators are scheduling their approval checks for every single parachain block. Yes, and
then so maybe already the block is created, but the validator also doing the verify job, right? Then those validator do some bad actors as reject the block on after the block is created. Any penalty on those validators?
a penalty for a validator that rejects the block after it is created. I assume by the block, you mean a parachain block, or you mean relay chain block?
A relay chain.
No, if as a relay chain validator, if you would reject a different relay chain block, it means that you do not import it. Like you simply ignore a single relay chain block, which is most likely a problem for you, because then you cannot, if you will be selected by Babe to issue another like block offer, another block on top of it, then you cannot offer on top of it because you rejected it, you haven't imported it. So you will offer it on the same height. You will essentially fork the relay chain. And then you will potentially be reorged out. It will kind of just punish yourself. You will essentially not be capable of performing the proper validator duties if you just kind of randomly not import and ignore a relay chain block. It's not really harming the rest of the network that much more than harming you. And it also has absolutely nothing to do with approval checking, as far as I understand. Because this is about, the validity of the parachain blocks. Okay, and I think we are slowly approaching the lunch break, right? No? How much time do you have? 1 more hour? Amazing. No, I have plenty of content left. And the whole security argument here is that it is technically possible to be lucky as an attacker, submit an invalid parachain block, and just hope that the first 30 checkers are your buddies, your malicious validators. But as I mentioned before, the chance of it happening is extremely small. And every single time you attempt doing it and fail, there is at least one honest guy, you will be very, very, very heavily slashed. And it would take you probably billions of attempts to find this one amazing situation where all of them were malicious. And problem is, by then you will already be financially ruined 50 times over before you can actually pull this attack through. Okay, and now we can look a bit more into the dispute stuff. So disputes are essentially started where a validator, where at least two validators disagree about validity of a parablock. We have definitely the backers that are saying it is correct. So if there's at least a single checker, an approval checker that says it is incorrect, we already have necessary elements to start a dispute. We are taking the backing vote, which is correct, and our vote, which says incorrect. We package those two and send it as a dispute statement. This is essentially proof that at least two validators disagreed. We can escalate the matter. This is like, providing a case to a jury or a court to actually solve and resolve and escalate. Question? Mike?
I mean, like only to what if, like in the tranche, I was assigned to this tranche, and I thought it's invalid. So I have to look for someone else to approve this for me. The dispute. So let's assume I'm a validator and I found in this tranche it's invalid, and I want to say this is invalid for sake of the security of the network, or I'm greedy and want to pick the reward. So I need to find someone else to approve that this is invalid as well, or how it could be.
We need a single honest guy. You don't need to have a quorum, a majority. You don't need to find a different validator to also say it is invalid. If you yourself think it is invalid, it's already sufficient to start a dispute.
So it's not the minimum is not 2.
No. You need one guy saying it is invalid and one guy saying it is valid. But you get the one guy saying it's valid for free from backing, because there's already at least 3 of them from there. So we simply take a backing statement and your statement saying invalid, and both of those are conflicting. It's enough to start a dispute. And as I mentioned, disputes break sharding. That's why we really have to be cautious when we start disputes. It's a major event. We have in Parity, we have bots that track if there's a dispute happening in Pocket Kusama, and every time there's a dispute, everyone's like, okay, alarm, something is happening. Either it's malicious or it's some kind of a bug. We have to investigate. We have to see what is happening. And disputes, they escalate. Now, instead of having the 30 checkers plus any tranches covering for no-shows, we are requiring more checkers to show up. In fact, we are requiring everyone from the active validator set to wake up and start checking. Everyone is recovering from availability, and everyone is publishing their statements, valid or invalid. And the moment we reach a supermajority, in our case, 2/3 of people agreeing that it's either correct or incorrect, this is the judgment, this is the resolution for a dispute. And this will always result in the parachain being decided valid or invalid, assuming a Byzantine threshold of 1/3, assuming 2/3 honest. Question?
Sorry, I'm asking so many questions, but you mentioned few minutes or 10 minutes ago, I don't remember, that if an active validator set couldn't finish all the work in their active session, they still assign or they have to deliver all the work. They cannot hand it over. So my question here is in the case of disputation, when you mentioned that we are asking all the active validator set to look up and still kind of double check this, it's the current active set or the one assigned to this block?
We live at this point in the blockchain world, and it's the active set at this specific height. The actual real world time has no bearing at all on this. Question?
Roger here. When a dispute happens, does that result in a event being sent to the blockchain so that you could like
Yes.
see, okay.
There is a dispute initiated event, I think that's viewable. You can subscribe to. There's also a dispute concluded if it actually finishes.
I was just wondering if it happens very often.
No.
No.
It's like it does not happen often, but it happens. Most of the disputes that are started are spam disputes, aka someone thought a parachain block is invalid, but it was actually valid. An example of that would be, imagine you're trying to run your validator nodes on a phone or something, on like a very potato hardware. The problem is, then you will, when you run the re-execution, the revalidation, you will time out. It will take you too much time. And you will say, oh, I believe this is invalid. It isn't, you're just really slow. And surprise, surprise, we have a few validators like that. I mean, at least we had, they got a bit slashed and punished. So pretty much, if there were any disputes in history, it was, I think in most, if not all cases, spam disputes. I don't remember, I don't think there ever was in history a dispute that concluded invalid. Like the majority, like the supermajority honest node said it is invalid and someone got slashed 100%. And this would be like the actually malicious scenario. Everything else is often, you can do malicious spam disputes, but they were usually accidental spam disputes.
Hi. So if the dispute arises, the scalability impacts all parachain or the parachain that is?
It affects everyone, the whole ecosystem, every single parachain, the relay chain, everything slows down because it's all of that is happening on the relay chain. Relay chain is the, the auditing layer of all the parachains. So if there is a dispute, all the relay chains validators are checking, and this can affect and can slow down the finality of every single parachain. So as a parachain, you are getting this like extra layer of security, the extra layer of finality. But if the relay chain is struggling, that you will not be getting it. And it's usually not the fault of a parachain. There's very little a parachain can do to cause a dispute. Like it's a completely a validator problem or a validator thing. Like this is not something parachains have to worry about. This is something parachains should observe, like as a metric, like how healthy is the relay chain? What is the finality lag on the relay chain? Are there any disputes on the relay chain? Because this can affect the finality of the parachain, but this is like weather conditions. You have little control over it. This is the external system that provides the auditing for you. And just to be clear, even though the relay chain might be lagging behind, the relay chain is just the auditing layer. Your parachain, your collators, they can still be producing blocks. It's a detached process. It's just you will not be getting those blocks audited and finalized by the relay chain. But you can still produce on your own, because maybe your parachain has their own like consensus layer that provides some security. The security maybe is lower latency, it's much faster, but it's not as like economically secure as the relay chain. So for low latency security, you rely on your own consensus. And for this very heavy security that's slightly lagging behind, you rely on the relay chain. Stuff like that is definitely possible, and it's like super customizable. Any other questions? Okay. So the dispute, we have to escalate to everyone to get the actual source of truth. If we ask everyone and we get the 2/3 majority on one side, assuming our Byzantine assumptions, we know that this is the absolute truth. This is the result we are actually looking for. And it is expensive to do, but if there's an escalation, it is worth doing. This is something suspicious. We have to fully verify it. So we can no longer just rely on the 30 checkers. We have to do the full thing. And if we get a result, either valid or invalid, someone is paying for it. Like a dispute has to be paid for. If it results in invalid, well, someone is going to pay a lot. This is a guaranteed 100% slash for the backer because the block was invalid and he was the one vouching for it. They are getting really heavily slashed. If it's actually valid, we are having a spammy dispute. This is this case where someone was trying to waste work of the network, or they have a potato node and they were just slow. In that case, they're also getting a small slash. So now we have pretty much the full picture of the ELVS pipeline. We go collect transactions, assign responsibility on the relay chain. One backer has to at least be there. We get the data in the data availability layer. We make it accessible, make it available. Then we do the actual verification. This is the, the cynical roll-up, the parachain magic, where only a small subset does the checking with escalations. And assuming there are no escalations, there are no disputes. But if there are, we dispense the punishments in the dispute layer. And the extra comments on the chain selection rule. So there will be more content later about the finality and other stuff. But when it comes to building on top, from the relay chain perspective, when it comes to building new relay chain blocks, every validator observes what is the state of approval checking. Are the candidates already approved or not? And the relay chain block producer will try to build a new relay chain block on a parent that doesn't have any blocks that are being currently marked as invalid, that failed in the approval checking process, or are being disputed. And also, actually, another note I should have mentioned, if a dispute concludes, not only we are slashing someone, but we have to revert. Like whatever happened in those blocks that were included, we are actually reverting the history that happened there. So if there was a single parachain that had an invalid state transition, and this parachain candidate ended up in a relay chain block, this whole relay chain block is invalid and has to be reverted. This is not a manual process. Everything is, of course, automatic. And there will be a new block built next to it, and the chain will progress forwards, ignoring it. And another cool quirk is the slashing. Because we are reverting, we have to essentially transplant the results and the proofs of the slash and the dispute happening from that specific fork that we are reverting from to every other history, to every other fork, because we want to avoid a situation where someone gets slashed in a single fork for losing a dispute and they escape to a different one. So there is a special extrinsic where we provide the proofs for disputes with all the dispute statements where everyone is voting, and those get transplanted to every single existing history of the relay chain. So there is no way you can escape the dispute. The disputes are across all the different forks. And one of the things with finality is the grandpa mechanism, which gives us finality. It will only consider and vote on relay chain blocks where every single parachain block included in them has already been approved by the approval checking process. So it waits until every single one completed approval checking, and only then we go to finality. Okay, and this is like implementation nitty-gritty details. We have this orchestration tool called Orchestra, and this whole ELVS part, the backing, the data availability, the disputes, and stuff like that is split into separate modules. There's a separate module for backing, separate for distributing statements, and all of them asynchronously communicate with using the orchestra tool to essentially manage all the subsystems and standardize the messages exchanged between those systems and signals and hooks. This is changing slightly in the JAM implementation. I think they're moving away from the subsystem module, but if you'll be looking through that code, then definitely focus on specific subsystems, see what messages are coming out, and then you can see, okay, this subsystem communicates with this one, those are the only messages coming out, and then you can see the structure forming. And I think there was a question.
Hello. Can we go maybe 2 slides back? Yeah. So we decided that disputed parachain block. So we'll just try avoiding them while forming the relay chain block. So the forming of relay chain block, is this assigned to maybe a single validator that they decide they form the relay chain block from all the available parachain block, all the valid parachain block, those are like checked, or do like everyone, every validator form a relay chain block of their own, and then maybe whoever's like reaches the most gets approved?
So we are using Babe, which effectively, in most circumstances, appoints a single block author. There was lectures, sometimes it's possible we have like 2 people under the threshold and 2 people will create relay chain blocks. But in most cases, there is a single relay chain block author per time slot. And this validator then aggregates all the statements, see all the backing messages, add all of that in the inherent, and they create this block and they distribute this block in the network. So every other relay chain validator imports that block and updates their local state according to whatever is in this block.
Hi. How many slashing does in real world occur on average? Is it a very rare event or it happens once a while?
Again, slower.
How many slashing does it on average happen on a year?
Okay, how many slashings on average per year?
Yeah.
I don't have a number, but very, 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 very little.
I remember only one in the past 3 to 4 years. Only one in one validator.
And the slashes that happened were extremely minuscule. And I think some of them, I also remember one, and it was for a slash type that is now even removed. So even this like slash that happened in the past would not be a problem nowadays. So it's very rare. I know that in Kusama recently, fun fact, the slashes for spam disputes are a pretty new thing. We didn't have them a year ago. And this is something I was working on. And we enabled them in Kusama not so long ago. And there were some spam disputes caused by some validators, and there were some slashes. But the slashes are extremely low because they're primarily just like shutting you down, disabling you as a validator to reduce your rewards. So the actual punishment isn't the slash, it's the reduction of your rewards you will get as a validator. But it's not many slashing events are happening. It's difficult to get slashed as an honest validator node. Okay, actually, I remember a different slashing example. There was a guy, as a node operator, you want to be reliable. You don't want your node to ever shut down, right? So what do? Let's spin up another instance of your node and have 2 of them. And then when one shuts down, the other will do the job. Sounds amazing, like very honest intentions, right? The problem is you have this is your validator private key, and you instantiate them both at the same time. They're both connected to the internet. And what happens is one of the validators got one of the messages a bit earlier than the other one. And when you are voting, when you're creating the blocks, they made a slightly different decision. One of them created a slightly different statement than the other one. They, for instance, didn't include one of the transactions. They equivocated. He made two conflicting blocks because one of them got the information a bit sooner. So this guy tried to be reliable, but accidentally he equivocated. The proper way to do it is to have two machines, and one of the machines following the chain, but not issuing any statements, and observing if the other machine is online and functioning properly. And if it shuts down, the other machine immediately picks up, but not have them online both at the same time actively issuing statements, because they might accidentally, due to timing reasons and network latency, equivocate. So, and this definitely happened. And the guy was trying to argue, oh, I was trying to be nice, and he was trying to cancel the slash through OpenGov. And I think it was rejected because everyone said, well, intentions were pure, but you just messed up. Please don't do it. So it's a lesson for everyone else to not do it.
I'm not sure I understand how quite a fork would work or a reorg would work in terms of like parablocks, just because at least from what I understand, like only one block, like one collation is sent to the backer, and that backer sends it, like validates it and sends it through the network. So would the reorg just mean like there's a chain in which a block doesn't exist for that slot?
You are quite correct that a parachain fork, when it already gets backed, is already quite improbable. It's borderline impossible. So the only situation that can happen is if you're having an aura on your parachain, that's having a fork is already quite literally impossible. If you're using some different consensus mechanism, maybe you have a parachain with proof of work, you can do it perfectly fine. Then you can have forks sometimes. And if you have a fork in this case, the collators will send two competing parachain blocks to the backers. And then the backers, based on, I guess, their preferences, whoever receives that first, will back one or the other if both of them appear valid. But effectively, only one of them will proceed forward through the pipeline.
Got it. And I think another thing I was wondering is, so this is for like one parachain, but like when we're talking about like 200 parachains, like even if one parachain block gets is invalid, not all the parachains can like move forward. So like one parachain does affect every other parachain?
Correct. If there would be an invalid parachain block included, this will potentially, this will revert the whole relay chain block, and someone will be punished. So yes, in this case, it does affect other parachains, but it has never happened in the history of Polkadot because the slash through it is millions of dollars. So yeah, if you want to revert a single relay chain block and pay the whole community like tens of thousands of dollars, you're free to do it. I think everyone would be very happy. It's an option.
Hi, I do have a question related with slashing. The backers are /2, right? But I do want to know if only the set of validators sort of responsible for the parablocks are / completely /, or also the voters that were backing this are /2.
So when we slash a validator, we are slashing everyone exposed to that validator. So if you are a nominator that staked $1 million with that validator, and this validator got slashed 100%, you are losing this $1 million. This is essentially the risk you are taking. Your job is to select trustworthy validators. If they did a poor job, then unfortunately, you made a poor choice, and you are also being punished for it. So yes, staking is not free money. Like, you are doing something specific. You're trying to find trustworthy validators. You're risking your money to potentially get rewards. It's not risk-free. No staking is risk-free if it's actually used for any sort of economic security. Same for Ethereum, same for all the other places. There are situations where you will be slashed, but just to be clear, slashes are incredibly uncommon because we build all those systems, we build all those security measures, so everyone knows that if they do something malicious, they get slashed. So ideally, all those systems never trigger because there is such a big deterrent. When you look at them, when you investigate them as an attacker, you may immediately know, oh, I cannot win. Like, it will cost me more than I will gain, so I will never even engage this system ever. Follow up.
Yeah, those, the answer is related with the nominators, right? But what about when this escalates to the rest of the validators on the relay chain?
Yep.
The voters is split. I mean, the validators is split between those that actually think that it's valid and the other ones that are invalid. So the ones that were wrong, which are validators, not nominators, get slashed too.
Good question. I get it now. So it depends. It depends on the result. If the result of the dispute was invalid, so we essentially decided that the candidate was incorrect, then the backer is getting punished 100%, and all the people on his side are getting slashed 2%. So everyone is getting slashed, just different amounts. In a case of a spammy dispute, so the dispute where the final result was, okay, the parachain block was actually correct, only the person initiating the dispute is getting slashed a tiny fraction. Everyone else we just ignore because it's not a huge deal. Someone has already paid a minor price and it's fine.
I want to ask about the time frame for the dispute. Is it like in rollup, like domestic rollup, like that takes more time? And also, like, what would be the incentivization for the active set of validator to participate in the dispute to double check? Are they getting any reward out of this?
So if I remember correctly, there is definitely a portion of the slash that is given to the people that's like reports the offense. I don't remember if it's given to all the people that participate and vote on the correct side of the dispute. I don't think so. I think it's just the reporter. I don't think as of now we pay any active rewards for the dispute participation. But ideally, we would be collecting your dispute statements and paying you for them, just like for any other duty of a validator. But maybe we do and I just forgot. Ideally, yes, you should be getting just paid for your work when you do the dispute checks.
Because if I am against, like, let's assume we have a dispute now, some people win, some people against, and in case of like dispute, like there is a slashing, everyone who's backing this one will be slashed. So it makes sense. If I'm behaving correctly, I should get something.
You are 100% correct. Yeah, there should be rewards for it. This is work being done that's helping the protocol, and it should be rewarded. The whole like reward system in Polkadot is that for an era, so for 24 hours, all the different activities you're doing as a validator, producing blocks, like offering blocks, providing statements, distributing items, they're earning you something we call era points. And essentially, at the end of an era, we calculate how much era points you have, how many you have earned, we compare it to others, and based on that, you're getting the new inflation rewards distributed based on that. So also, if you get like the very, very minor slash, it disables some of your responsibilities as a validator, which reduce the amount of era points you get over time because you don't get to participate in some of the activities.
And the time frame for disputes?
The time frame for disputes, they conclude quickly, a matter of 6-12 seconds-ish. It's not a 7-day period like in optimistic rollups, no. Because in optimistic rollups, they're essentially afraid that no one will do the work, so they give you a freaking 7-day period to actually provide the proof. We do explicit checks here. Everyone does the checking, so we quickly, in a matter of pretty much 6 seconds, like approval checking finishes up in like 6 seconds, even less than that. The whole process, and then we have a verdict, correct. It's not an optimistic rollup where maybe correct, 5 hours later, it still may be correct, and you have to wait 7 days to be like, okay, yeah, it's good enough, it's correct. You're getting a quick feedback loop that, okay, we have 30 people that put their money that this is correct. We have very good crypto economic security that this is actually correct. We can proceed, we can finalize immediately. And then even if there's a dispute, it's still an extra. Approval checking can take like up to 6 seconds. If there is dispute, an extra 6-12 seconds to wrap it up, and we're usually done. But it also depends how many other disputes we also have. If we have like a full-on dispute storm, when there's like a bunch of disputes happening, this process can take a bit longer.
Hello. So how we decide like the amount of token like percentage being slashed, like, or we need to like lower their reward rate? How we decide? Is there some governance system that decide?
There is me. I am figuring some of the slash amounts, and there's some people from the pre-foundation like Jonas and researchers like Jeff that generally try to come up with some of the values. Some of them are easy. For instance, approving a malicious candidate, like backing in a malicious candidate, this is like very clear that this is the most malicious thing you can do. This is like explicitly trying to double spend. So 100% is not, there's not much extra thought process behind it. You're just getting the maximum possible punishment. Some of the other values which are a bit more complicated are, for instance, the equivocation, slashes for equivocations. I was talking about it in one of the previous lectures that for equivocations, we don't slash a fixed amount. It's dynamic. We slash based on how many other equivocations have been done in this specific time slot. Because a single equivocation usually is not a major security threat to the system. Sure, it's an unnecessary message, it's annoying, it's weird that you have done it, but it's not an immediate problem. You didn't try to like double spend and actually do something super, super bad. But if there is a lot of equivocations, this can really slow down the network and have some very adverse effects. So they came up with this, like, I would have to look for it, but there's like a function where you input how many equivocations we have in this time slot, and it's like an exponential and it grows. Someone from a pre-foundation, I think it was Jonas or some researchers, have come up with this function that it scales sufficiently high, and they figure out exactly how many equivocations are dangerous to the system. Like, when does it start becoming a problem? And they like fixed this function to ramp up very rapidly, roughly around this number. And there are also some slashes like the spam dispute one. And the spam dispute one, it was pretty clear we want this to be a very small punishment because it can accidentally happen to honest nodes. So we cannot go crazy and go 100%. It has to be minor, and that's why I opted pretty much for a near 0% slash, but it reduces your error rewards. So it's, instead of just slashing you, we just reduce your income. So a lot of debate, a lot of discussions, different slashes had different people responsible for it and trying to figure it out, but there is not like a single magical formula to decide it. We have to always figure out what is at risk, what is being actually affected by it, and is it possible that an honest guy can be affected by this slash? If yes, then we have to be cautious. If no, then punish as much as you want.
One more question. So if any new validator want to like join the ecosystem, so what's the process for that? Like for new validator, if any new validators want to like join the ecosystem, like to validate the chain, so what's the process for being selected as a validator?
Okay, so to be selected as a validator, you essentially need to have a lot of stake, like either a lot of stake being nominated to you, or maybe you have a lot of stake of your own. And then you participate in the validator elections, we are hoping that the staking miner, the fragment election stuff, actually selects you in the winning election, and then you make it in. The problem is, if you're a completely new person with no stake, then how do you get the stake? How do you get the reputation? It is actually pretty difficult. I think there was a 1,000 validators program from Web3 Foundation, and it is possibly still running.
And we're not running this anymore. We are
Okay,
running
never mind.
a new program with decentralized nodes. And basically, the foundation is delegating stake to send you in the active set. This is rotational, and they are selected in periods. You have to meet certain criteria like uptime. You have to demonstrate that you have the necessary hardware and these kind of things. Yeah, but this is the gateway to validate and get some rewards in the ecosystem, especially if you're new. And the idea is that when you are in the system and you're new, it's okay. But the idea that is you build your own reputation, and you should do also some kind of marketing if you have your own brand and your own on-chain identity. And eventually you can have more stake that is no more part of the foundation, but is more part of your BD and network, and also like community and stuff like that. Yeah.
Yeah, so just to be extra clear, this is a temporary solution as a new validator. Like, it's not that Web3 Foundation is funding every single validator. This is just so you can attract some organic nominations, gain some reputation, momentum, and then Web3 Foundation retracts the extra funding because you can actually support yourself through your own reputation and nominations given to you. Any?
Yeah. So, assuming a parablock is found to be invalid, what would happen to all the other parablocks in that relay chain block? Will they be put into a fresh relay chain block?
Good question. No, they are just getting dropped. So they will have to be resubmitted, and every transaction that was in them will unfortunately have to be resubmitted. Would be nice if they would be getting like automatically picked up again, but it's not the case. Maybe a place for further development and optimization. But yet again, this is something that only happens in very edge cases, and pretty much we never have the invalid parachain block, so it pretty much never happens. Would be a sensible thing to have, but it would add a bunch of complexity.
Can I open a dispute if I'm not in the active set of validations?
No. It's just the privilege of being a validator, because the problem. I mean, actually, I'm not 100% sure, because if you would have two conflicting statements, so a message signed by a validator saying it is correct, and a message signed by a validator saying it is incorrect, technically we don't care who provides this extrinsic to start a dispute. This could be provided by a non-validator, assuming those conflicting statements are given. I would need to actually double check if non-validator can submit it, but there is little value in it, because yet again, we only need a single validator from the 1,000 to actually submit it. But yeah, even if it's not the case, we could make it like that, and that would be perfectly fine. But then it opens us to potential spam attacks where someone tries to promote a bunch of disputes, and there is little we can do to punish that guy. So there have to be a higher fee to even run this dispute, starting extrinsic and stuff like that.
Hi. So I have a question related to chain selection.
Closer.
Oh, is it okay? Yeah. I have a question related to chain selection rule. Like you said, if there's a dispute in a transaction, and if it's actually invalid, the block will be dropped. But if it's in a forked chain, is it something like the chain will the fork chain is something that we have to select?
So If it is invalid, then we simply select a different one. We build a new block, or we select a valid one. If we have a normal, like organic fork with no invalid stuff, which can happen, we usually just, it's up to the block author, the next relation block author, to select which one he wants to build on. I think he simply builds on the first one encountered, but he prefers blocks built by primary authors. So remember that every relay chain block is either built by the babe selected primary author or the secondary fallback aura author. So he's always preferring the primaries as a potential parent for the new relay chain block.
So if the transaction is invalid, will the chain also will be dropped, or will just it will just be the block?
If the transaction is invalid, will it?
Will the chain, the fork chain on which the block with invalid transaction is, will be dropped, or it will be just the block?
If a transaction is invalid, it will not necessarily, I mean, it will kind of fork the chain, because the relay chain block that included the invalid transaction will have to be reverted, and a different relay chain block on the same height will have to be created. So it is a fork. We're discarding one and we're creating a new one, hopefully this time with correct transactions.
Okay, go ahead.
Another question related to the point when we have a dispute, successful dispute. You mentioned that all the blocks after should be reverted. The block that had a dispute and any block after should be reverted. And I'm just like concerned about what the parachain should do, because like if we have a parachain with a high throughput, and the nodes or the collator has maybe like they are setting the prone setting to be to get rid of to erase the blocks after like 10 seconds or whatever, and the dispute happened, then how they can like kind of regenerate the transaction or get the transaction to be included later? Is it like when we revert the block in the relay chain, the validator job to rebuild based on the correct parachain blocks, or the relayer, sorry, the collateral in this case has a new job to kind of like reconstruct everything from the beginning? I can say it again, like let's assume we have a dispute now and we have 100 parachain, and the dispute happened, and after we kind of like finished it, we have 2 blocks after it. So we will revert all the work happened in all the 3 blocks. So we have so many blocks from 100 parachains. So whose job to kind of like reduce these transactions, and what the parachain should do in this case? Should they consider when they proning their data to consider this case or not?
So in this case, the collators will simply start producing blocks on the most recent correct, like finalized block. So they will revert the 2 blocks and look at the mempool and start adding, like collating new transactions. And then it is kind of the responsibility of whoever submitted transactions to resubmit them. So if you have an application and you wanted to send some funds from Alice to Bob, you send it and it tells you like you're waiting for a confirmation, gets into the mempool, you get a confirmation, and then you say like, maybe not loading, but it's not yet finalized, it's slowly going through the cycle. And if it failed on the relay chain and it was reverted, then at this point in the application, this person should see like the transaction was extracted. And the application kind of has to say, you have to retry or something like that. We are not like magically getting the transactions and replaying them. A user in this case, if there was actually a full on-chain revert, it depends on the application. The application maybe can schedule it for you and do it automatically, but I feel like most of the applications in the ecosystems would essentially tell you error, something happened, please retry. I think this would be a pretty standard way. Yeah.
We have one more, Mateo, we have one more question. Then we stop, or I can give my piece.
Yeah, let's do like last one, and I will be available for 3 weeks and on the breaks and everything else, and we can continue discussion. Last final one.
Hi, my question is, because parachain can have a specific mechanism for the consensus to finalize the block, if parachain use kind of proof of work consensus mechanism, which means the finalized is probabilistic, right? So which means it can be reverted. Does it make the finality that submit on Polkadot, I mean on the relay chain, become incorrect? Especially if some escalate happen in the relay chain, which parablock will be validated to check which validator is malicious and who are not. And if no escalate happen, does it affect on what happened of the parachain that the finalized block is not same with the submitted on the relay chain?
So if you have a parachain with a proof of work system, it's perfectly fine and you can have it, but it has to be slightly modified and tweaked. Because in a proof of work system, you're getting probabilistic finality packaged with it, but you still should observe the finality of the relay chain, which then audits your blocks. And if your parachain block got finalized on the relay chain, then you essentially have to make it irreversible on your proof of work chain. Even if someone uses a lot of work and remines on a different like fork from the past, doesn't matter. So the relay chain finality probably has to take, it has to take precedence over the proof of work. You only can use proof of work to figure out which collations to submit to the relay chain, but in the end, the finality comes from the relay chain and not your probabilistic finality of proof of work. Okay. We have like 10 minutes until the break, right? Cool. So we'll quickly start the next lecture. Shouldn't be particularly long. Then we'll have a break. Any sort of questions or discussion we can have, and I'll finish the talk after the lunch break. Okay. Agile Coretime. Who here has think they understand what Agile Coretime is, or have they heard about it? Any sort of familiarity with the topic? Raise your hand. Actually raise it, not like a tiny bit, I want to see hands, thank you. Okay, good. Let's look into it then. So, Agile Coretime is a collection of features. All of them are actually already live on Polkadot. I was giving this lecture many, many times, and every single time I was giving, oh, this thing is coming soon, this thing is coming soon, and finally I can say, we finally have all of that stuff. And we'll be looking into exactly what different features we have and what they allow, and why we even built such a thing. But generally speaking, this is a scheduling mechanism for how parachains and different tasks on Polkadot are assigned to execution cores. Essentially, this is an interface for how you get access to execution cores, how you buy your privilege to use them and get your stuff audited by the relay chain. And we'll be, some of the features, not to go too deep into them, but we'll be having items like, if the slide loads, we'll be having items like bulk auctions, which will be the main source of your Coretime or Coretime tokens. But there will be also things to get more flexible core time, like on demand. And we'll be looking into core time marketplace where you can exchange it and different ways of renewing your core time. All of those are essentially methods of accessing execution cores, leasing them, exchanging them, and making them as flexible as possible. So even though I mentioned that we have all of those features already live, it's still not a fully finished thing. There is still some work being done, some items on the agenda to make it more robust, to make it more flexible, or to make it more performant. So things might change in the future, and things are actively changing. But at least you can play around with all of them already, and they are being used by real projects, real parachains in production today. A good place to read about it is the first RFC1 Agile Core Time, where you can read the original description of how it was imagined. And as you all remember, I showed you the fellowship repo in one of the lectures yesterday. And the fellowship repo has two main folders in it. There's one with the runtimes for Polkadot and Kusama. This is where the configuration happens. And the second folder is RFCs, requests for comments. This is essentially design documents prepared for the Polkadot protocol by the community, not only by the fellowship, but usually by the fellowship, where they describe major protocol changes or additions and essentially ask other experts or random anonymous people, if they have some feedback as well, to comment and point out any potential flaws in the design. Then those RFCs are voted in OpenGov to potentially approve or not approve or request changes. And then the RFCs are actually implemented by the community, by parity, by the fellowship into the protocol to make changes in it. And Agile Core Time went through the same process. They did initial design, scope, there was a lot of discussion, many things changed, approved through OpenGov, and worked on by parity and others to ship as a product or as a feature. And another disclaimer, Agile Core Time is actually a prerequisite for Jam. Like, we had to get it out for Jam to even be possible. So it's another example of, yeah, Jam is this new thing, but it will be using and leveraging a lot of the tech we already have in Polkadot, like Agile Core Time, to make its cores available. Because Jam will also have this concept of execution cores that will be utilized by different applications. Okay, so first, let's look at the Polkadot protocol and figure out, like, okay, so what is the product here? What is Polkadot actually offering? And I don't mean like what a specific parachain is offering. If you have a gaming parachain, sure, they're offering a game, but what is the Polkadot protocol as a whole actually offering? Anyone has like a, hopefully not a 10-sentence explanation, but like a quick one? No ideas. Interesting. Okay. The idea is we are offering computation, we're offering core time. And this computation can be pretty useful because it's not the same computation as you would have on your local machine. If you have your phone, if you run a game or a process there, that's it. It's very hard to verify. It's not a trusted execution environment. The computation we are doing here, the computation we are auditing on the relay chain is backed by the consensus of this whole system, is backed by millions of dollars. Whatever computation you are actually running there is very probably correct. You can see every single step of it and inspect the inputs and the outputs and know for a fact that it cannot really be easily tampered with. And because Polkadot is sharded, it allows us to provide a lot of computational. A lot of programs can be run on Polkadot and benefit from this high security. But the problem is, how do we actually price and make this computational core time available to different sort of applications. And a lot of them are sovereign, a lot of them have different needs for how much computation they need. So in the past, we had a system of parachain leases. It was a pretty simple process where essentially as a parachain, I will not be going super in detail into this, but as a parachain, you were buying up an execution core, buying up a privilege to have a parachain block every 6 seconds for 2 years. You essentially had to commit that this is for how long my parachain will be running. But the problem is 2 years is a pretty long time, a very, very long time. It's many, 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 many blocks, and businesses don't immediately want to commit to such a long time. There are some things that, some projects that want to experiment for a shorter time, some projects that maybe didn't need this many blocks. They wanted more flexibility. So overall, the whole mission of Agile Core Time was to waste less computational, waste less core time. If someone requires less computation, let's actually give it to them. Also allow for max higher throughput, because if you waste less, then we can better utilize whatever resources we actually have right now. And to lower the barriers of entry, because not everyone wants to commit and pay pretty much upfront for 2 years of core time, of block space. This is simply too much. But a good thing about the previous system is that it was maintaining some price predictability, because, well, if you pay for 2 years upfront, at least you know exactly what you'll be paying for 2 years upfront. If you compare it to something like Ethereum, where the gas prices fluctuate every freaking block, every second, you cannot really estimate how much you'll be paying for gas, how much you'll be paying for computation the next week, the next hour, the next month. You cannot really estimate your costs that much. So like maintaining this price predictability was something we really wanted to keep. And also, the whole leases were a bit more complicated. It wasn't as simple as you pay this much and you get it for 2 years. There's a whole complicated system on top of it with crowd loans, and you were loaning the money from other people and paying cost of opportunity and stuff like that. We wanted to just simplify it, makes it easier to understand. This is how much you are paying, that's it. Okay, and with those like tenets and missions, we will now be slowly exploring the different features and parts of Agile Core Time, starting with bulk auctions and a few different ones. But I think it's a good time to go on the break now, and we'll dive into that after the break. Okay, thank you. And a half ago or so, which was discussed for a long time between the Web3 Foundation team, different ecosystem actors, and Parity, that makes some noticeable changes to this process, which is, and this RFC is not yet implemented, meaning that the future design is not exactly what we have today. What we have today is pretty much what I have in the slides, and I will link you guys the RFC that's in a pretty nice way explains the new model, and I will mostly try to also give you some pointers of what the new model will be doing. Okay, and out of curiosity, has anyone here heard the term Coretime Baron? Raise your hand if you heard this Coretime Baron. Okay, some people heard it. There was an interesting event in the Polkadot where someone tried to essentially attack the network, and it forced us and the community to adapt the Agile Core Time system to be more robust towards such attacks. But anyway, let's get into it. So let's first look into what is actually being sold on bulk auctions. Bulk auctions, instead of selling a 2-year-long period of core time, are selling a 28-day-long period. It's much shorter, still pretty long, but we'll get into why a bit later. And exactly, what are we getting? We are getting for 28 days every 6 seconds, you are getting a parachain block. If you buy it, you have the right for this thing. And a single block, remember, is just a bit of computation, 2 seconds of single-threaded computation on reference hardware, and 10 megabytes of I/O. This is what a block is. If you want to run a program on Polkadot, as long as your program uses this much of compute and this much I/O, you can run it there. And the method it is being sold with is with Dutch auctions. Were Dutch auctions covered at all at the introductory first few days? No? Or PBAX? Do you remember that stuff? Okay. Short story is we start with a high price. The price quickly drops down. If someone says, I am buying, they're buying it at the current price. It was a model used for tulip auctions it's Dutch tulip, well, in Dutch. And they essentially had a big clock at the center of the hole, and it was starting with a very high price, and it was ticking around to a lower and lower price. And whoever raised their hand first was buying it for whatever the clock was saying. And then they were moving to the next batch with a new high price and going again and again. So it was a very rapid, quick auction. And where do the funds go? If you actually buy some Coretime using those Dutch auctions, bulk auctions, where is the money going? So the situation here is that it is simply burned. There was a lot of discussions if you want to send this money over to the treasury, if we want to allocate it to somewhere else, but allocating it to the treasury creates a lot of extra game theoretic problems. If someone is buying a lot of Coretime and the money goes to the treasury, but they also have a lot of dots and they control how the treasury spends those funds, it can create a lot of weird, vicious cycles. So we wanted to simplify the process, and it is simply burned. And the whole pipeline is that we essentially start with some kind of a maximum price. In a Dutch auction, you need to have some maximum, and we slowly descend to a lower minimum price. It will initiate at some price X, and the Dutch auctions will linearly over time decrease to the minimum price. The Dutch auctions are taking a few days, so it's not as short and snappy as the actual tulip auctions were. You still have plenty of time to place your bid, and you can see the price linearly decreasing over time. It will look in the current system something like that. We are starting with a pretty high price and somewhat linearly decreasing to the target price, and then to the minimum price where we stay for some time. But the thing is, isn't it just leases repackaged? Instead of 2 years, we have 28 days and nothing else changes? Like, is it actually that big of an upgrade? It doesn't end there. There's more stuff we can actually do here. So previously, if you actually bought the 2-year-long lease, there wasn't much else you can do about it. You assign it to a specific parachain, and well, you have a lease for 2 years for that specific parachain, end of the story. There were some attempts in very specific situations where if you go to OpenGov, go to governance, and you escalate a problem, you can maybe transfer your lease to a different team if you explain yourself and stuff like that. But all of that was very bespoke, very specific, and not easy to organize, and the community had to really support you in this decision, so you better have a good justification. This time, what you're buying is not yet assigned to a parachain. You're just buying a right to 28 days of call time. You're buying a call time region, a call time NFT, let's say, and then you can actually exchange and switch it around. You can go to an external market and transfer it over. So teams that don't want to deal with those actions can potentially just rebuy it from a different source. If there are just speculators that can use that market and buy those tokens to do some extra stuff with them. And it's not just exchanging. There's even more stuff that you can do with them. They're partially programmable. And we can, for instance, interlace them. So interlacing allows us to make our core time much, much more flexible. In a normal situation with no interlacing, a parachain will kind of look something like this. You have a new parachain block every 6 seconds as time progressing, nothing extra specific, nothing special. And I hope that the name interlacing kind of already suggests what this feature might actually be doing. It's allowing us to schedule multiple parachain, multiple different tasks onto the same execution core, and they essentially take turns. So we can schedule 2 different parachains, and they are taking turns. So first we're getting the block from A, after 6 seconds block from B, and then another block from A. This is increasing the block time for them, but they're essentially more effectively using that core, especially if none of those 2 parachains required a full core to begin with. It was too much throughput for them. So they can actually save on resources, save on money by sharing essentially a lease. And interlacing is achieved through manipulating the core time region. This is like this NFT mask. They essentially have a bit field of who produces a block on that specific time slot, on that specific execution core. So the bit mask for 2 parachains sharing a single core would look something like this. We are having some, on the first one, the B mask suggests parachain A actually is making a block there, and then they are taking turns. So if you see a bit mask 1010, it means it's producing a block every other slot. And interlacing is not just limited to 2 parachains. We can actually push it much further. If you want to have 3 parachains, 4 parachains, 5 parachains, whatever, as many parachains as you want. If you want to have a situation where parachain A produces 3 blocks in a row, and then it doesn't produce any blocks for 6 blocks, and then again 3, you can do it. It's customizable. So you can actually tailor the amount of core time, block space, and throughput you have to the exact needs of your parachain. And how do you actually practically edit those regions? Where do you edit those masks? Where do you plan and schedule all of that? And this is where secondary markets come in. So Agile Core Time has secondary markets, and it's not an afterthought. It's not like we build a system and it's like, oh, now some other people will build some applications. Secondary markets and this ability of this NFT to be traded, programmed, and exchanged and cut into pieces was there from the beginning, from the first RFC, where we wanted to give it back to the community so they can build the tools and the scripts and the UIs to do anything they want with it permissionlessly. I think the most popular secondary market and UI interface for manipulating, buying, reselling, and working with Agile Core Time is RegionX. It has all the necessary tools you need there. And most of the features I will be talking in this lecture are available through RegionX as an interface you can work with. If you press S on the lecture, it will give you notes, and the website URL for that is pasted there. Okay. And some of the features you have on those secondary markets is just an option to purchase a core. Then you will actually try and buy on a bulk auction and access to the full execution core for 28 days. You can also view all the regions you have currently bought and then interlace, split, and exchange them. And you also have options for auto-renewal, which we'll get to in a second. You can also view the current state of the auction that is running. How far away has it progressed? What is the current price? Where are we on the curve? Okay. So what if, committing to 28 days is still a lot of commitment you don't want to go through? Maybe you want to schedule your block every 10th, but it's still something, every 10th slot, but it's still something you have to commit to in advance. You're committing for this month-long 28 days period of blocks. Not everyone wants to do it, and sometimes it's impossible to predict how much compute you will need a month from now. So we need something that's more dynamic. And have you guys heard the term parathread being used in the ecosystem? Raise your hand so I can actually see it. Okay, very few people. So this meme is becoming less and less and less relevant, which I really like, because it was very relevant a few years ago. We like having multiple names for the same stuff, but generally the term we're using nowadays is on-demand parachains, on-demand Coretime. The old term that is still sometimes flowing around is parathreads, which I wouldn't worry about. So the main limitation of interlacing is that you need to have a long commitment. On-demand Coretime tries to give you a more immediate answer to how do I get Coretime if I need it now, if I need it in 5 minutes, where do I go to? Or maybe if you want to tinker in Polkadot and do something for a very short amount of time. I just want to play around for a bit and then move away. I don't want to get a full-on lease. And on-demand is very, very similar to something like AWS spot instances. This is something you don't rent out for a long time. This is something you get instantly for now. So you do a bit of compute, a bit of execute, and then you immediately go out. Sometimes you will pay a bit premium prices if you want to do it on a very short notice. But if you want short notice, that's the price. And you can already start noticing that this whole thing with AWS, there's a lot of similarities, like both AWS and Polkadot is effectively allowing you to do some compute. And this is for a specific reason. They are actually offering similar services. So we are trying to create similar interfaces with on-demand, where you're buying the spot instances, with bulk, where you can lease your instances for a longer amount of time. So on-demand allows you to purchase a single block worth of Coretime. You're essentially buying the audit for a single parachain block. And you can do it on a very, very short notice. The moment you put the order, you put the extrinsic to get the rights for it, you are getting that within like 6-12 seconds. And then immediately you can produce a collation, and this will be audited by some backing group and then approval checkers, and you will go through the whole process. And then your execution call will be then repurposed for someone else. So you're just buying it for this single time slot. And there's a bunch of different use cases for that. You can create temporary parachains, things that spin up quickly, do some work, and then die down or go to sleep, hibernate for a bit, and maybe wake up later. You can do projects that maybe they don't get that much use. So you essentially batch a bunch of transactions, a bunch of calls. And when you get enough, you batch them, create a single block, and then go to sleep again. You can just temporarily start up something, make a few blocks, make a few state transitions, figure out if it's achieving what you wanted, figure out if it's working as you expected, and then shut it down without any major costs or effects. Or you can produce low latency applications that sometimes you need low latency, but you are not able to buy a full execution core and have a block every 6 seconds. So essentially, you're waiting until you get this important transaction and then buy a single block. So we quickly get it out and wait for some time extra. And on-demand will become relevant a bit later in the lecture, and I will go back to, because there are a few extra use cases, but we need other features to actually show them. And there are some dedicated execution cores specifically for on-demand purposes. So there is a separate price for getting the on-demand cores, independent of the bulk auction price. And that's being dynamically updated based on how many on-demand orders there are. Okay, and now elastic scaling. So we covered some examples where you maybe don't need that much throughput, you don't need a full execution core. What is the opposite? The opposite of having more throughput, like requiring more throughput, requiring more than a single execution core. If a single execution core is not enough, then how do you scale then? Like a relay chain, as I mentioned, can only validate a single block, and your I/O is bound to 10 megabytes. You cannot just scale your collators because the relay chain validators will not keep up, so it's not an option. And like this is not just a hypothetical. There are actual chains in Polkadot that require more than a single core, that have enough transactions to need more space, more throughput. So the way it works is if you would have a single parachain, we have like 2 different parachains here and 3 cores. Let's assume C doesn't use up all the throughput, and A is actually completely starved for space. Like it's running out of space, it's using all the computation or the I/O. There's nothing else it can do. And even though the second core is empty, well, the first one is completely blocked. There's nothing we can do in this case. We are not properly utilizing all the resources. So the idea is that scheduling the same parachain to multiple cores, but it will not create 2 separate chains. This is not what we want. We want to schedule the same parachain to 2 cores. So instead of looking like this, it will look more like this. They're essentially being provided in a sequential manner. One core will be before the other, but if you remember the PVF, to verify a PVF, all we need is the list of transactions, the previous state, and that's it. So as long as both backing groups get the relevant previous state and the relevant transactions, they can actually validate them in parallel. Of course, if the first one would fail, then the validation of the second one would also be invalidated because it's dependent on the first one. But we can validate them and then do the confirmation check later. We generally, in most cases, limit elastic scaling to 2, 3, up to 4 cores. This is where you're getting most of the throughput benefits. It will like quadruple your throughput on the parachain, quadruple your I/O. So the benefits are quite noticeable, but of course you have to rent multiple cores, so it's also increasing your costs. You can push elastic scaling further. There are experiments being done with 12 cores for a single parachain. It's not increasing your throughput that much. It's primarily to reduce, either boost the I/O, which is definitely there, and to reduce the block time. Because with 12 cores, you can essentially publish 12 parachains block per relay chain block. So a relay chain block is every 6 seconds. So if we have 12 parachain blocks, it's half a second block time for a parachain in this case. And a lot of I/O. Okay. So remember how we discussed the old auction system and the old model? It wasn't perfect, but there was one property people really, really liked, and it's the price stability and predictability. So as I mentioned, that's the gas prices on Ethereum, and you can definitely see some very noticeable spikes. Either CryptoKitties or any other smart contract was released, super popular, and suddenly every other business is getting priced out because they can't compete with CryptoKitties that's consuming all the and boosting all the gas prices, and your business is running out of steam. So that's a no-go for any serious business where they cannot estimate their actual costs. And that's why we created renewals. Renewals is essentially an extra mechanism connected to bulk auctions that if you already purchased a core, you have some extra privileges in securing that core again, in renewing your lease, in renewing your ownership of that core. They are not perfect. You cannot keep it hostage forever. The price will still keep increasing, but at least you know that as long as you pay market prices, no one else can snipe it for you. It's not a matter of, oh no, someone sent a message quicker than me and I lost it. You will have preferential treatment on actually obtaining it, assuming you're paying some market prices. And The whole idea is that we are moving from this paradigm where every single core has a single parachain, and we're moving to something which is much more dynamic and much more flexible, when parachains actually share cores, interchange, where multiple schedule the same one, or multiple parachains to multiple cores, or a single parachain to multiple cores. And all of those features combined have a lot of extra effects that are not visible immediately. For instance, we have a bunch of cores being provided to the on-demand pool. But what if the desire for on-demand is much higher than that, and the hard-coded cores are not enough? What is possible is you can buy the book auction leases, the book auction NFT, the regions, and provide them, submit them to the on-demand pool to effectively expand how many execution cores are being provided for on-demand. And if you do it, then you're also getting some percentage of the profits coming from on-demand. And more interestingly, on-demand works with elastic scaling. And I think this is the feature a lot of the parachains have been really excited for, because you can have a single execution core and essentially have some kind of a script or an overlay that detects how much traffic there is on your parachain. If there's a lot of pending transactions in your collator mempools, you can essentially have a script purchase extra on-demand cores temporarily, and then immediately elastically scale, add them to your parachain. So you temporarily, for a few blocks, have 2, 3, 4 cores. You consume the backlog of transactions, and then you actually scale down back to 1 core. Stuff like that was definitely not possible before, and working together with on-demand and elastic scaling allows you to build stuff like that. There's also all of the Coretime logic, the book auctions and everything. Most of that stuff, as we mentioned with the minimal relay chain initiative, we're trying to move stuff away from the relay chain. So there is a dedicated system parachain called the Coretime chain, where a lot of that logic and the broker for organizing those sales is actually happening. On the resources page here, if you press S, there's a bunch of links where you can read the original RFCs, where you can see some of the tools or blog posts that explain it in more detail. Are there any questions about Agile Coretime? Question there?
I have 3 questions. So feel free, if it's a lot, I can skip some. The first one is related to the interlacing thing. Is it like fractionalizing NFT? So I'm giving kind of like part of this NFT to other parachain, and we are utilizing them? Because it's mentioned in the slide, it's kind of an NFT. So like each slot assignment or the Coretime is representing in an NFT. So are we fractionalizing this NFT to represent the ownership of, or the authority to do it?
Effectively, yes. We are kind of splitting it into pieces, and maybe one parachain takes ownership of a small section of it, while the other a different one. If you add them all together, like the bit mask should be all ones, effectively utilizing all of the.
The core itself is kind of mapped to this NFT, or I'm just like having one NFT for the 28th day?
There is generally like a single NFT for the whole period. If you interlace it, if I remember correctly, it does split it and create like 2 separate ones, but I don't remember exactly what is the implementation for that.
My thought here, like, what if I missed one of the, like, it's kind of like a theoretical. I know like there is no economic incentivization for this, but I might miss one Coretime. In this case, I will not be able to use it, this NFT. because like it's as if I'm buying number of slots for this time. So if I missed one in the second, in 12 o'clock, I'm not able to use it, use it in 1 o'clock, for example.
You missing a block does not stop you from.
I mean, like, let's assume I as a parachain, I have one slot here. I can submit my block here, and I didn't use it for whatever, like outage, whatever happened. I will not be able to use this NFT later. It's not used, but the time passed.
Yes, they expire.
Yeah.
Like they're for a specific amount of time. You cannot store your Coretime regions forever. They're for a specific amount of blocks that are well specified in time. It's not just any sort of moment you can redeem them for.
For the elastic scaling thing, when you mentioned the Moonbeam example, where they need more than one core slot, and what if, what's this, like, I just want to make sure I got it correctly. So we are validating both of them, and then if they are kind of like, there's a conflict between of them, we are detecting this in the auditing phase where like we are validating the block. Is it correct?
So we are evaluating both of them, and one is dependent on the other. But whenever they're providing the collation, they're already giving us all the necessary state to run the state transition. So all we have to verify the correctness after we verify the correctness of each individual one in the void, we also have to check that the result of the first one matches the starting state of the second one. Like this is the simple comparison there. And if we have that, everything is working fine and we can proceed as normal.
Thank you.
Hey, it's Shlok here. So my question is like, who determines how much core time a parachain should be assigned? Are there any some benchmarks? Like parachain decides itself, or it's decided by relay chain?
I mean, you get as much core time as you buy. Like whatever amount you want to buy, this is how much core time you have. That's why we have the auction, and whatever you can essentially afford, this is how much core time you will be getting. Generally speaking, I think absolutely out of sheer laziness, people are just getting one core because it's the easiest, it's the least amount of clicks. There's plenty of cores. We can add even more cores. So core time is not particularly scarce right now, except some specific events in the past where it was a bit scarce for some short periods of time. So a lot of people are, whenever starting a parachain project, they're just getting a single core and coasting on it as a safe, simple solution. And then if you need more, you elastically scale to more cores.
All right, my name is Femi. So how do we see the notes on the slides? You mentioned
S. You press S. Like
yes, okay. I thought it said X. Okay, yes. Secondly, why did you decide on using the Dutch auction method? Why not other methods?
In the past, we had candle auctions, which had some nice benefits. Exactly why have we chosen Dutch auctions? I don't remember the exact line of reasoning. The good thing with Dutch auctions is that they allow all this whole process to run a bit faster, and the bids, it's not as easy to front run, which we wanted to prevent. Because the moment someone purchases something, it already is established, set in stone, and that's it. And Dutch auctions were quite fitting for that. I think you definitely could build the system with a few other auction types and it would still be perfectly fine. There were actually some discussions to maybe bring back the condole auctions. So you can make arguments for a few different implementations, for sure.
For the case of on-demand core time, with the parachains purchase core time when they have a ready block, or any time is okay with them? Like they're the ones to decide, because they wouldn't want a case where they have the core time and then maybe they get like one transaction after a long time, and then they submit like a block that's not full. Wouldn't that be like a waste?
It would be a bit of a waste to submit a block with a single transaction, but it's much less of a waste than having a full execution core making block every 6 seconds and all of those blocks completely empty. And there were some parachains in the past that had little transactions, and there were some parachain blocks being issued with no transactions at all. So on-demand essentially allows you to at least publish those when you actually have some transactions instead of all the time.
Okay, so you've said some blocks were being submitted when they're empty. Does that mean the blocks are submitted automatically? Or
Yeah, in most cases, the blocks are being built by collators every 6 seconds. And if they're collecting the transactions from the mempool and packaging them into the parachain block, into the collation, and sending them over. In a situation where the mempool is empty, they're essentially packaging kind of nothing and sending that as a collation. It's just progressing the height, it's progressing the time. Maybe there are some hooks it's running when we get to a certain height, but there were no specific transactions being executed there. Any other questions about Coretime?
When you're interlacing transactions between two different parachains, how important is it to know the structure beforehand? Or like, do you set the structure of like how the two parachains put their transactions on the score? Or like, why is it important that it's like this?
You absolutely do not care about the structure of transactions. This is essentially what you care about is like the ratio of block production. Are we taking turns? Is it, you know, A, B, A, B, A, B, or is it A, A, B, A, A, B? You care about stuff like that. What exactly is in the transactions doesn't really matter. It's just some opaque blobs that will be re-executed on the relay chain. We do not care about it that much.
The reason why I was thinking about that is like for elastic scaling, I guess it talks about like how you want to like be putting transactions on like two cores equally until the end. I guess it seems like maybe it would be better to fill up one whole core like as much as possible and then go to the next one when you need it. And then like maybe if there was a way to pay afterwards for how much extra core space you're using, that seems nice if it doesn't matter what the core is actually doing or like what it was assigned to.
This is what you can achieve with on-demand plus elastic scaling, is essentially only reserve one core, and whenever you essentially fill it up, on-demand buy an extra core with on-demand, and then use elastic scaling to use temporarily 2 cores when the overflow goes to the second core, and we no longer need the second core, you stop buying it through on-demand.
Got it. I thought in the on-demand you had to buy it like 5 minutes before. I don't know if I read that incorrectly.
Go again?
I thought you had to buy the core 5 minutes ahead of time. I thought that's what the slide said.
You have to buy cores ahead of time in bulk auctions, yes, but with on-demand you can buy them quickly.
Oh, okay.
That's the whole thing that on-demand gives you, is the spot instances where you can very quickly on a short notice within a matter of 6 seconds buy low amounts of core time.
Okay, sorry, I read this wrong. Okay, sorry, that makes sense.
Any other questions? Here.
It's another follow-up question regarding the point when you mentioned that the NFT for the slot is like kind of tied with the time. So what could be the situation where we have a fork or something like this? I will lose my NFT in this case because like the time passed, or it's kind of linked to the block number itself.
It's connected to the block number. Like nothing ever is connected to the time. It's a blockchain, everything is connected to the block time. Like we just translate from block time to like real world hours sometimes, but everything is in block time. Even all the referendums, When I say 24 hours is the, the active validator set duration, it's not actually 24 hours. It's whatever is the number of blocks that 24 hours roughly is. Any sort of time I am using, everything is counted in blocks, everything, always, for every single question. Any other questions before we proceed? We good? Okay. Then I will actually show you the fellowship RFCs. So if we would go to the Polkadot fellowship repo, which is just, repo is Polkadot-fellows, or if you Google Polkadot Fellowship GitHub or Polkadot Fellowship repo, you'll find it easily. There are a few main things of interest in this space. There's the runtimes, as I mentioned. This will be the Polkadot runtime configuration, and this will be the Kusama runtime configuration. And we also have the RFCs. If we take a look at RFCs, we have a bunch of stuff here. There is the manifesto, which essentially outlines how RFCs should be structured, what is the mission behind the whole fellowship. And in the text folder, we have some of the documents describing the designs, so all the different RFCs. And we have the RFC number 1, which is the Agile Coretime, which is the original design. And we also have RFC number 17. Let me scroll up. RFC number 17, maybe I'll make it bigger as well. RFC number 17, which outlines the new redesigned market model with a few changes compared to what I was talking about a moment ago. And if we go into it, we have a small summary of what it actually does, if it loads in a second. And some of the motivation for what the changes are. And there will be a formal, but not super mathematically, I cannot understand it, formal explanation of this new model. The main differences with this new redesigned model is that in the past, the renewals had a very fixed schedule of how the price was adapting. So if you manage to secure a core for very, very cheaply, you were essentially paying like 105% if you wanted to renew, and then 105% again. So it was slowly, slowly ramping up. The problem was if you bought your core time for like $1, the 105% of $1 is still pretty much nothing. And then 105% of that is also pretty much nothing. So it allows you to hoard it for very long. If you manage to buy core time for like a single cent, it's kind of maybe not infinite, but you can stretch it out for a really, really long time. So this redesigned model essentially ties the renewal prices to not just the price you bought it at and nothing else. It ties the renewal prices to the market prices. So if there is a very, very high demand, your renewal price will slightly go up. It is still bounded with some limits of how much it can go up, but it will react to the market pressures. But nevertheless, if you can pay the market prices, you will always have priority to get it. And the market prices, as I mentioned, they're bound. They're not going to be skyrocketing a few 100% in a matter of hours or days. It's at most, if I remember correctly, around 10–15% increase per month or something around that. And I highly actually recommend anyone interested in this like core time stuff to actually take a look and read that RFC. It's pretty nicely structured.